Hi, my name's Paul Browning. That's me there. Before I had kids, the years have not been kind, but I don't have an up-to-date picture. I just wanted to talk briefly about IP subnetting and the new course I've just created, just finished today actually, called IP Subnetting 0 to Guru. So it's designed for people who don't know anything about subnetting or know a little bit and are a bit confused, which I'm sure around 80% of people I've met who are studying for IT or already in IT are still a bit confused about subnetting or just can't do it very quickly. This is it springs from a course I created many years ago. It's had 210,000 views nearly, and it had a website. This website no longer exists actually. It's all on a new website, which I'll tell you about in a minute. So yeah, it's 12 years old, this course, so I basically had to just redesign it from the ground up and add a whole bunch of new stuff, which, as you know, IT is moving very quickly. Why should you bother learn subnetting? Well, most people avoid it, and I think they think it's hard, and the way most people teach it is hard actually. Unfortunately for you, if you want to pass an IT exam, you're going to need to know subnetting, and around 5 questions out of 60 for these exams certainly are going to be around subnetting. So definitely the Cisco CCNA, and the exam's adaptive, remember, so if you start getting questions wrong, they ask you more of them. If you get them right, then the computer works out you know what you're talking about, and it'll move on. 5 questions out of 60. If you work out the percentage, which I'm sorry I didn't in advance, so I'm not sure, this is the difference between passing and failing, knowing subnetting. So I kind of hope that gives you a strong case for learning. Now, some of the things you can do if you do know subnetting: if you're working on the help desk or as a network engineer, you're probably going to have to fix subnetting problems, and things like this happen. Most of the IP addresses on a commercial network, at least, are assigned by DHCP. At some point in your career, somebody will turn this off by ticking a little box because they've watched a YouTube video, and they will add their own IP address. And the chances are that's in use by somebody else on the network, or it's in the wrong network. Now, you're going to have to troubleshoot this. You're going to have people watching you, and you're probably going to have some angry bosses and customers watching or listening. So if you don't know subnetting, then you're going to really struggle to fix this kind of issue. Technical job interviews. Almost any IT job, even if you're programming, doing security or wireless, part of your technical interview will be subnetting questions. I had to do exactly this. I had 2 senior engineers actually with a whiteboard writing subnetting questions for 1 hour when I had a job interview for Cisco. It was pretty tough, but I'd taught myself subnetting, so this is the method I'm going to be teaching you. Modern subnetting, you need to know a lot more than we did when I first started, which is why the course has been created. Obviously IPv6 now was kind of a tiny percentage, maybe 1% of any exam back in 2006. Now, I don't know, sort of 45+% consists of IPv6 because we're phasing out IPv4 slowly. And then the dual stack, you need to know about this, which is covered actually in the course briefly. It's running 2 IP addressing systems. You need to know how to subnet your network. So if you've got a big network, you need to know how to chop this into smaller chunks. So you manage this chunk, another engineer manages this one, another engineer manages this one, and also you'll need to know how to advertise your routing protocols, which I show you how to use IP addressing to advertise the correct networks. You can create network designs and addressing plans. There's actually an entire career as a network designer. I'm thinking the Cisco Certified Design Associate or Professional or Engineer. These are network designers. You need to work out private IP addressing systems which are free to you to use, and then how to get them to convert to routable addresses. This is known as network address translation. You need to know how to configure pools of addresses on your DHCP server. So you could have pool 1 goes to the HR team, pool 2 goes to the admin team. If you don't know subnetting, you're going to struggle to get all of this working. And this is, I tell you now, this is your day-to-day stuff. It's not something you won't be doing often. You'll be doing it pretty much every day if you're working on a network. You need to know how to configure wildcard masks on routers and firewalls. I'll show you how to do that. So this is based on a book I wrote a few years ago called Subnetting Secrets. This is actually going to be from tomorrow no longer on sale. It's going to be IP Subnetting Zero to Guru. But I just wanted to show you that it's actually been doing really well, this entire method, on Amazon. There's 56 reviews, most of them 5 stars, a few 4 stars. So this has helped a lot of people. It used to be a video course as well on a different platform. So I'm going to show you how to work out binary and hex numbers, work out IPv6 and IPv4 basics, address the classes and CIDR. Don't worry if it doesn't mean anything to you, I'm going to show you how to do it. How to design network addressing for your customers or your boss. Great wildcard masks. You'll need to know these for your routing protocols and for firewalls. And then how to answer exams super fast in the exam. I'll demonstrate videos of me showing you how to do it in under 30 seconds, which is the way you want to answer questions in exams or technical interviews. So put a bit of effort in. It doesn't take too long. The course is around 4 hours. Then I'll give you some extra time to do some exams and working out on any project. And then you want to spend around 1 month, an hour, brushing up and just reviewing, just doing some practice questions. Most engineers don't bother, and then they just look silly when it comes to interviews or when they are faced with a live problem. You also must learn IPv6. I'm going to show you all of the basics. This is stuff every IT engineer should know. It's not an advanced course, but I'll show you the addressing basics and some of the stuff you need to know. Now, I might put this video actually on YouTube, so I'll put the URL here. It's www.howtonetwork.com, and the course will be under TCP/IP. Look for IP Subnetting 02 Hero, and I'll see you on the inside. Welcome to the exciting world of binary math. If you, like me, you probably only covered this in school and sat there in the lesson when you were aged 10, 11, 12, whatever, wondering why the heck you had to learn this silly counting system. And unfortunately now it's come back to haunt us. As IT people, we need to understand a little bit about binary. But the good news is it's a fairly simple counting system in as much as it only uses 2 values. The complicated thing is when we try to convert these 2 values into a number that we recognize as humans, i.e. decimal. Now, the reason why electronic equipment uses binary is purely because if you have a wire, and this is your wire here, with the termination on whichever end, the only one of 2 things can happen to this wire. You can have no signal traveling on the wire, or a signal. No signal, signal, no signal, signal, etc. So in this particular instance, this would produce a value when it reaches the destination of 0, 1, 0, 1, 0, 1, 0, 1. Now obviously this is measured over time, so you could have 2 values of 0 together, or 2 values of 1, etc. So at the other end of the, say we've got a computer in this end here. I have to subject you to my 3D efforts. It would receive this piece of information and make some sort of use of it. We'll come into counting in a bit. Obviously this is happening in a rapid fire rate, and you could receive thousands of bits within a second, and then it would accumulate these bits to, for example, receive an IP address or start compiling an email, etc. So this is why we're in this situation that we are. And certainly for Network Plus exams, CompTIA CCNA, CompTIA A+, and most other networking exams, you will need to know this. And unfortunately, years ago they used to test you on how to convert decimal to binary and then hexadecimal, which we'll come to later. Then they stopped, and now they're doing it again. So my advice to you is learn it, because it's pretty easy to learn and you only need to learn it once. So we need to know how to add up in binary, and we just count the number of 1 or on values that we're presented with. Now what we do for our conversion is we have, if I draw a chart here, we take the number 1 as our pulse, and then all we do is double it. So 1, 2, and then I'll show you later, but we would keep doubling it. And each column here represents a binary value. For example, if there's 0 and 0 in our two columns here, obviously the final value is 0. If we have a 1, an electrical signal here, and no electrical signal, then that would equal the number 1. If we have a 1 in the 2 column and a 0, I'm sure it comes as no surprise to recognize the fact that it's number 2. And then finally, if we had 1 bits on in either of these 2 columns, that would equal 1 plus 2, gives us 3. So you can see the concept is fairly easy. Obviously what becomes complicated is when we have more values, and then, as you may already know if you've seen IP addresses before, we have values stuck together with other values to produce sets of numbers or groups. And then even worse, those groups of numbers get compared to another group of numbers, which is an IP address gets compared to a subnet mask or a wildcard mask, which we'll come to later. As network engineers and IT people, we will be concerned certainly for the next few years in with octets. Now an octet is 8 binary bits grouped together. So this is what is an octet. We've got 8, 1, 2, 3, 4, 5, 6, 7, 8 places here. And we start with the value number 1, and then you can see we double it 1 to 2, 2 to 4, 4 to 8, 16, 32. Now, if we were counting in groups of 10, obviously it would carry on past 1 to 8. And we'll need to be able to do that later on, but we don't need to worry about it at the moment. So if we have this octet here, on all of the available numbers have zeros in, they have no pulse, which is possible, then our value would be 0. Now, if we get another octet come through, and each has a value turned on, what we do is add 128 to 64 to 32 to 16, 8, 4, 2, 1. If you added those numbers together, and I recommend you pause this video just to prove it to yourself, so don't just take my word, you add all these numbers together and you'll get the number 255. Now this number may look familiar to you if you're already, or if you've been studying IT or you're working in IT, you may well have seen this value, and especially so if you're familiar with using a packet capture software where you're looking for certain types of packets or problems on networks, for example broadcasts. And then finally you could have a couple of values turned on and then some of the values turned off. So if I added these together, 12864 is 192 plus 1 equals 193. You can come up then with any number including 0 and up to 255 inclusive, just by turning these bits on and off. Now what I recommend you do is practice some of these yourself. Just write out some of these 2-row 8-column tables here, and practice some of your own values. As I said, you only need to do this kind of stuff a few times before you get the gist. Now, the rules, there's something called an RFC. I'm not going to write it out in full. This is called a request for comment. I think that's a really strange term, to be honest, but RFCs are documented suggestions for how various internet working concepts will operate. For example, EIGRP comes from a request for comments. RIP, multicast networks, private networks, all these things are come from RFCs, and then obviously people give feedback and say what will work, what won't work, and then it gets adapted, changed, updated, or sometimes they just get completely shelved or become obsolete. So the RFCs have devised how our IP addressing works for IP version 4, and there's a large number of them. But one of them suggests that to get subnet values, we'll do a particular thing. This particular thing is our ones will be contiguous. This means you can't have, for a subnet value, you can't have something like this. Your values must all run together. So if you have a 1 anywhere, it must be next to another 1. Then you can have a contiguous set of zeros. So you could have that 1, 2, 3, 4, 5, 6, 7. You could have that, no problem, as long as all of your on values here are together. You can't have an off value in the middle. So this is, hopefully, will be a light bulb moment for some of you. Add all these values together, and obviously we've only got the 128 value 128. This is a possible subnet value. We can apply this in one of the octets on our network. So remember, we have to keep the ones together. So if we have 2, if we add 64 and 128 together, we get 192. If we add another one, if you add 32 to 192, which is a quicker way of doing it, and if we keep going, we've filled in another value here, 16. If we add 16 to this value here, we get 240. So all these numbers, I hope, are looking familiar. If it doesn't look familiar, it doesn't matter. We add 8, so 248. So you can see that each time we're adding a smaller value, but it's still a value. We add 4, 252. Oops, sorry. Next we add another 1. So 254, and you can guess we're going to add 1 next. So I'm sure you know what the next number is going to be. All of the possible values equal 255. If all of your values are 255, I'm going to come to this later, but if all your values are 255 for your network, this is a broadcast. The RFCs, one of them, has said in order to send all of the traffic to all of the hosts on your network, turn all of the host bits on. I don't really this. I'll explain all this more in detail later. If all of the host bits are on, this is a broadcast. If all of the broadcast bits are off, if all of the host bits are off, sorry, that value equals the subnet. Now this is important, and we'll come to why it's important later, but this number and this number, the broadcast number and the subnet number, we can't use to add to hosts. For example, 192.168.1, that's our network number, 0. So say this is our host part of our address, and these are all network parts. If all of our host numbers are turned off, we know this is the subnet. So we can use this for a routing protocol, but not a host number. Alternatively, if the very last octet for network hosts is 255, so all the bits here are turned on, what this tells the network is this is a broadcast packet, and every other single device on the entire network will receive it, and then it must stop what it's doing and process that packet. So this is what slows our network down, because one of the things is process and broadcast packets. Alright, so we're setting the foundations here, and what we are doing is drawing the worst triangle ever. We are building a pyramid of knowledge. At the bottom, we're doing binary, hex, and decimal. And then we'll later talk about IP address classes, subnets. I might have missed some of this out. VLSM. So we're building a table of information. CIDR. I'll put some there for summarization. So it looks a bit like the sorting hat from Harry Potter, but I've just been watching that with my kid. We're building a pyramid of knowledge. And what happens is a lot of engineers, IT engineers, they can add IP addresses, and they know how to write an IP address in the CIDR value, which we'll cover later. But they'll write the IP address here, and then they'll say, oh yeah, that's /24. What they don't know is this stuff down here. And I've written the book to go with this course. What's it called? Subnetting 0 to Guru. They don't know all of this stuff. And I've gone into major companies, like these guys are managing the software, all of the hardware for the air traffic controllers, and they don't know this. So this is pretty shocking, because what this means is you can't troubleshoot network problems, you can't design an addressing scheme for a customer. All of these things will go wrong for you if there's a problem, or you're asked to go into a business and do this. So this isn't going to happen for us. We're going to start building our table on a very strong foundation, build our pyramid of knowledge, and then until finally all of this stuff is just easy for you. So thanks for listening to me. I will see you on the next presentation, where we're going to cover some more numbering systems. And welcome to Hexadecimal. What is hexadecimal? Well, we need to learn it, I suppose, is the first question, or why bother? It's covered in the exam. If you take any networking exam, certainly CompTIA exams, also Network Plus, A+, and it's heavily used in IPv6, which, as of recording this video, is ubiquitous. It's on almost every network. You may well be using it at home and not realise already, if it's enabled on your network card, and about 50% of internet traffic is using it. So you're going to be out of a job if you don't understand hexadecimal and IPv6. So the fundamentals is made from 16 different symbols, which we'll come to in a moment. It's supposed to be more user-friendly than binary, but I'll leave that to you to decide. It's what's known as a base 16 numbering system. So to put that in perspective, binary is base 2, which we've already seen. We've got these possible values here, and obviously decimal is base 10. There's 10 values for decimal. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the 10 values, and obviously if you go to number 10, then it's using the 1 and the 0. So the human beings obviously use decimal. We use it for all of our numbers to telling the time and measuring lengths and stuff. The reason why we use this is obviously we learn to count. This is obviously the worst hand ever, but most of us have got 4 fingers and a thumb on each hand, and this is how we first learned to count before we ever had even an abacus. So don't know if you knew that, but yeah, this is why we use the base 10 system as human beings. So hexadecimal has values. The values range from 0, and then we move through letters from A to F. So 0 is included as a value, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then obviously in decimal we jump up to 10 here, but here we move into the A, B, C, D, E, F. Now it's important you know this, because sort of exam questions, they may ask you something really simple like tick all of the possible values for hex, and they could be putting in letters like X or A, B, C, D, E, F. They could be doing something like G. So it's important you remember that it's 0 to 9 as numbers, and then the letters A, B, C, D, E, F. If you count all the way across, it's 16 values in total. Now each hexadecimal value is actually can be represented as 4 binary bits. 4 binary bits is known as a nibble. You don't often hear this term actually, but somebody obviously invented it. Maybe somebody was thinking about food at the time. But if you invent something, obviously you get to name it, and this person named it after food. So it's called a nibble. Now 1 nibble is half a byte or 4 bits, and we said earlier that 8 bits is a byte, so half a byte is known as a nibble. I only mention this because A, it's interesting, and B, I have very occasionally seen exam questions asking this. Alright, so mapping hex to binary and binary to decimal. As I said in the previous presentation, this used to be in the syllabus, it disappeared for years, and now it's back. I kind of ran out of space here. I'd like to have had this all continuing off to the end, but then it'd be too small for you to see. So you could actually, I recommend you write this out yourself, but you just have decimal, hex, binary, and then go all the way across. So you wouldn't have this bit here. So obviously we know how to count, and we've got 16 values. If you count 0 as the first value, then obviously we're going to end at 15. Hex 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then each value is worth a nibble. This is the nibble here. So 0 is obviously all the zeros, 1 is just got a 1 in the 1 column. If you add the first 3 values, the 1, 2 and 4 together, you'll get 7. And then finally we get up to here in the 8 columns turned on, the 10 and the 2, and so on. You've already covered binary, so if you're still a bit stuck on that, then please go back to the previous lecture. Alright, so converting binary to hex. Converting binary to hex, what we need to be able to do is convert this in any of these ways. You could be asked a decimal number, and in the exam they could say convert it to hex. You could be given a binary value and asked to convert that to either hexadecimal or decimal or both, and indeed the other way around as well. So you need to be able to do any of this. Obviously it's pretty easy when we're using the numbers. So if we are using the counting numbers from decimal, then pretty easy. But when we get to the value C, for example in hexadecimal, then it becomes a little bit more difficult. We've got to remember our decimal, our binary and our hex table, however you want to write it out. And then obviously we'll start off with our when you're writing your table, a 0, binary, hexadecimal, and then we'll go all the way up. And obviously you can stop at value F for your hexadecimal. So you'd get to 16 and then 1, 2, 3, 4, sorry, 15. And then 1, 2, 3, 4, which is 1 plus 2 plus 4 plus 8, 15. So counting in hex, this, if you're working out a hexadecimal value, and say for example you were given 1A in hex, how do you work it out? Well, remember in decimal, to work out binary, we went 1, 2, 4, 8, and then we added our binary values here. In hexadecimal, it's a 16-bit numbering system, so we go, the first value would be 1, the next 16, 16 times 16, 256, 256 times 16, 4096, and we can add values down here, our hexadecimal values. I've kept it easy, so we've been given the value 1A, so we will write 1A here, so we've got a 1 in the 16 column and then an A in the 1 column. So it explains actually here as well, this is an extract from the book. So we've got 16 obviously, and then we need to add another value to 16, and if you work out what A is here, it's 10. 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A is worth 10. So 16 plus 10 would give you the value 26. Working out binary to hex. What you would do normally is break your binary into nibble values, and these are all your nibbles here, as I said, just 4 binary places, all zeros, all ones, or a combination. So you're given this binary value here, and you can basically just break that into 2, as we did just here. Alright, so 1111 is 15 if you worked out if you added these values together you would get 15. And 15, if you wrote out your little chart down here, 15 in hex is F, it's your last possible value. 0011, you've got a 2 turned on and a 1 turned on equals 3, and in hexadecimal 3 is 3. So sorry, I didn't realise that I put that pop up there. So our value in hexadecimal would be F3. This value here, if you've broken it down, it would map to F3. F in the 16 column and a 0011, 3 in the 1 column. Working out hexadecimal to binary. So what we've got here, I've just written out the hexadecimal chart here. We've got our 16 value, a 7 in here, and a C in here. So what we would do is split the two values. So in the exam they would say 70 in hex is equal to what in binary, or they could say decimal obviously. So a 7, and then you would map out a 7 here in binary. You would map out a 1 and put the two values together. So the answer would be 0111, which is here, and then 1100, which is just here. Alright, so I've got a quiz. I think you should really spend about 10 minutes a day for just a few days to work out some simple hex to binary, binary to hex, and all of these combinations, only because it's a mark in the exam that you're going to miss out on if you don't know how to do it. So thanks for watching. I'll see you on the next lesson. So welcome to our presentation on IP version 4. I'm just going to put some fundamentals in place, so forgive me if you already know them all. If you only know some of them, then it's definitely going to be of use to you. And if you don't know any, then congratulations, because you're going to learn a bunch of new stuff. IPv4 is currently in use in the vast majority of networks all over the world. Now this is changing, and this is the last quarter almost of 2018. You really need to get up to speed on IP version 6, which I'll touch on I think towards the end of this course. Really need to learn it in good detail though, because it's the future. So at the moment still, most networks you will be working on and supporting will be using IP version 4 mainly. We're gradually phasing into IPv6. At the moment, we're in IP version 4 mostly still. We're going to move into, we're not going to suddenly change from here to here. So what's going to happen is IPv4, and then we'll be doing a dual stack where we're running both IPv4 and IPv6 on your network, which means you'll have to support both, unfortunately. And the idea is if things aren't working well with IPv6 or there's an issue while you're adding it to your network, all of your IP traffic will still continue to flow. And eventually we will, IPv4 will go the way of other technologies such as IPX, SPX. You probably haven't heard of that unless you've been in IT more than 15 years. This was an old addressing system that was used on networks, and you had to know how to support it. Token, ring, all this stuff. It was just awful, but we had to know it for our Cisco exams. Alright, so this is, if you check the URL, you can basically Google the term IPv6 traffic, and probably the top result will be this here. And this is basically given the adoption from back in 2019 all the way up to the start of this year. We're actually late 2018, so we're probably along here somewhere, and looking at the way the chart is going, probably up here. So this is the amount of traffic that is on the internet that's currently using IPv6, and you can see around 1/4 of it is using IPv6. So it doesn't really take much of a genius to work out that you need to be able to support IPv6 probably from now, at least understand it. And I think I'll come to it in the next slide actually. I've had a CCIE, since you're probably watching this course on howtonetwork.com as a member. You really could do with going to courses, TCP IP, and then checking out the IPv6 course. This was done by a CCIE who's a really smart guy, and what we're doing is teaching you. There's 3 levels, so at least do level 1, which is beginner, level 2 is intermediate, and level 3 is advanced stuff that will take you into the higher echelons of IPv6 support. Start with level 1 at the very least so you understand all the basics. You do need to know it for interviews, and you do need to know it for most IT exams. So an IPv4 address, what is it? It's 32 binary bits, and remember we've covered binary already and we've covered octets. So instead, I just want you to understand this. The computer or server reads exactly this as I've put it here. It reads 32 binary bits. It doesn't understand anything else. When you're programming, say you go into Windows and you're doing coding, not coding, you're adding an IP address, you'll do it into 4 octets, but what the computer will do behind in the coding, it just convert it into a load of 1s and 0s. It doesn't understand anything else. But to make it easier for us, we'll break it into 4 octets. Now we separate these, each octet, by a dot, or you may call it a period in other countries. The IPv4 addresses are assigned by the IANA, Internet Assigned Number Authority. These actually will allocate numbers to ISPs, and then your ISPs will be allocating it to you or your company. Here's an example of an IPv4 address. This is actually a non-routable address, which I'll come to in a while. It's a private IP address. Now, in binary, if you had to work it out or write it out, remember we've got our 8 places, and each value is doubled, so we have a 1, 2, 4, 8, 16, 32, 64, and 1, 2, 8. So this is what this represents, just as a refresher. The first 2 bits are turned on, all the other bits are turned off, so 128 plus 64 gives you 192. And then it'll be the same. You can work this out in your own time for the other columns. Now, if you wrote this out on a Cisco device, or you had to type it in on Windows, you would type 192, there'd be a full stop, or there'd be another block, another grid here for you to put the number in. But on Cisco, you would just write out the number, but with dots in between, or periods. So that's how you'd write it out, and you would add a subnet mask, but we'll come to that later. So this is a Wireshark capture, and I recommend giving you a list of things to do here, but I want you to be a good network engineer who's confident and you can breeze through all the interviews. So I recommend you learn how to use Wireshark, and yes, there's a course on howtonetwork.com. But we're looking at this information up here, like the source, the destination, protocol, but particularly the address on down here. So you'll see this address here, which in the OSI layer is your network layer, and then it gets encapsulated into a frame, and then the frame gets encapsulated into all of these bits on the wire. So this is what's actually happening, although obviously it's converted into a format that we can recognize. The powers of 2, we're going to be using this an awful lot as we go through the course, because this is what unlocks the answers for you for exam questions and technical interviews. I did cover it earlier, but it's your powers to your 2 to the power of whatever. So 1, 2 is worth 2. 2 to the power of 2 means 2 times 2 is 4. 2 to the power of 3 means 2 times 2 times 2 is 8. And basically it carries on here, so 2 to the power of 7, and you'll keep going down. You can go down, I think we'll go down to about 10, maybe 16 places actually when we're working out our subnetting, which we'll come to later. Now, IP addresses are actually grouped into classes when they were first allocated, and you think that when this was first all devised, people didn't have computers at home. It would cost however many, I mean, you've got to allow for inflation, but say equivalent would be like $1 million for a computer, and it would take up the size of an entire room, and people could actually walk inside the computer. If you look at early images of early computers, they'd walk inside and replace transistors in there and massive circuit boards. That's how big they were. So you certainly wouldn't have one at home. So addresses were allocated into groups. A Class A was allocated to very large organizations, like thousands, tens of thousands of employees. Large organizations received Class B address, and then smaller organizations would be a Class C. Now, Class A address is the first octet is reserved for the network address, the last 3 for hosts on the network. Now, the network addresses, you will know if you're ever looking at a problem, and we're going to be, don't worry, we'll come to this later, you will know what class the network is by the first number. And the first number, if it's a Class A address, will range from 1 to 126 inclusive, any of those numbers. You may recognize the 127 number. You can't actually use the 127 address on any networks, and one of the addresses within this network, 127.0.0.1, is actually reserved for loopback testing. If you ping that address on your PC, it will test to see the TCP IP stack is working correctly. Now, how do network devices who don't look at numbers in decimal, how do they recognize that it is a Class A address? The first bit on the first octet must be set to 0. So this is the first octet, and we've got octets 2, 3, and 4 will be down there following. This first bit here must always be set to a 0. That's how the network device and PC knows that it's a Class A address. Now, the very first number we can use, we can't use a 0 for a network number. So the very first number, if we turn it on, is a 1. The very last number will be a 1 in every single column here, apart from the one that we have to have the 0 in. We can't put a 1 in here. So that tells us what our network numbers can be. Our very first network number can be 1. You get 1 all the way up to 127, which you can't use that number, so let's call it 1 to 126. This is an example of a Class A network. Immediately, if you won't see this obviously up here when you're doing any configurations, but you will see the first number, which will tell you that this is a Class A address. So to get the host numbers, when we're working out our hosts on our networks, we start at the far right to get the number 1, and we keep adding all the numbers available until almost all of the host numbers are used. So if we used our 10 address, remember this bit's fixed here, and for example, we've been allocated this address by our ISP. This is actually a private address, but it's just an example. So this is our network, host, host, host. We start off at the end here, and we start adding numbers all the way up. So the very first number available would be number 1, which is a 1 in the 1 column. And what we could do is then add the next number available, which would be 2, then 3, then 4, then 5. And all these values here, these host values, could be filled up with numbers until almost every value is filled except 1. What this is the last host available on the 10 network. And we'll do a lot more detail in this later. This is the last available host because if all of these numbers are turned on, so we've got 1 in every single host value, what this means is it's a broadcast. And every single host on the 10 network must stop, process this packet, this broadcast packet, to see if it's the intended recipient. So it will go out to every single host, even though only one of them is the intended recipient. All right, Class B addresses. So the first 2 bits on the first octet are set to a 1 and a 0. These have to be set. This is how network devices know that it's a Class B address. What this will do, if you work out the values, if I've got a 1 here, it's definitely going to be 128. And if you turn on every other number available, it gets you 191. If you had every number off over here, it would be 128, which is just here. Alright, so here's an example. This is a Class B address. Now you'll notice something different. The first 2 octets are reserved for network numbers. The second 2 are hosts. So we've got 16 8 binary bits there plus 8 binary bits, but remember 2 of them are reserved. So what we'll have to do is say we've got 6 bits available for network numbers here and plus 8 in the next column. So if we get 2 to the power of 14, that equals 16,384 possible networks. It sounds like a lot, but we quickly found out, or the IANA found out, that they were going to run out of addresses very quickly. Host numbers, it's a bit better. We've got 2 to the power of 16 bits, 8 bits here, and 8 bits here. And that's equivalent, it's equals 65,536. Now we have to take away 2 numbers. One number we have to take away is the subnet value, and the other number is a broadcast on the subnet, which we'll be talking more about later. Class C addresses, the first 3 bits on the first octet are set to 110. That gives you a possible range of network numbers from 192 to 223. And here we have the 110. If you add those numbers together, you'll get 192 for your network. If we turn all the available numbers on that are left here, obviously we can add these two here, we get 223. And here's an example of a Class C address, and you'll see the first 3 octets this time are reserved for the networks. So this will give you over 2 million networks. Hosts, though, we have 2 to the power of 8 hosts, which is 256, and we're not allowed to use 2 of the numbers, the subnet number and the host number, so it gives you 254. Class D addresses are used for multicast traffic. Don't ignore it because it's actually used for protocols such as RIP and OSPF to advertise networks and listen for networks. Also used for video streaming services and other services that you could dial into, for example a webcast. The numbers, you should make a note of this, available are 224 to 239 inclusive. And finally, Class C addresses, these are used for experimental uses only, never used on live networks or home networks. Here, private IP addresses, these were actually defined in RFC 19. I mention this because I've had customers call me and say, we need help using our RFC 1918 addresses. And the first time anyone said this, I had to quickly Google what they meant because I'd never used that term before. But what they're referring to is, if you check the RFC, it's private IP allocations for networks. What this means is there's a range of network addresses that can be used for free by you at home or on your network. The only things you can't route it over the internet. You can't send any of these addresses over, so you can't host a website on these addresses because people can't reach you at that address. The reason being is there could be thousands of other people using the same addresses. These are the available numbers. Any network number beginning with 10, obviously that's Class A, 172.16 to 172.31 inclusive. So any of your network addresses start with these. If it's 172.15, it's not private, you'd have to buy it. If it's 172.31 inclusive. 192.168.1.1, 192.168, any network starting with that address. Now here's a kind of summary of what we've talked about so far, which numbers we have to start with. Which octets are reserved for the network, first octet, 2 octets, and then the first 3 octets. And obviously you can see what can confuse people sometimes. There's the first bit here, which the computers start off counting from 0 to 31. There's 32 values altogether. Alright, so cover some fundamentals here. You need to understand these because I presume you understand this as we go through all the other presentations. Thanks for watching. Make sure you take the exam and I'll see you on the next lesson. So let's start getting into the rudiments of subnetting. Don't worry if none of this really makes sense. We're going to be going through this whole process many times over and then we'll finally start streamlining it. But there's a longhand way, as you can see, and a shorthand, or what I call the easy way, to subnet. Now which method you choose depends on the particular circumstances. If you're designing networks for a customer, then you're going to probably use the longhand way, and this is verifying everything in binary or using supporting software that's designed to allocate networks, subnetworks, IP addresses, etc. And this will normally be kept in a secure location online on your network, so it can be retrieved by other IT engineers. And you've probably got weeks or months to go through the entire process. Now, if you're in charge of IP address allocation at work, certainly for larger companies, there'll be someone whose role it is to allocate IP addresses and subnetworks to the company, and they'll be part of a committee or project team or whatever that looks at the business IT needs and expansion. For example, if you're adding another office somewhere, adding a remote office, or expanding or buying out another company. And then writing design documents also. Shorthand way, you just don't have time. So if I put here, you've got maybe weeks, and here you've got minutes. This is the paradigm we need to think about. So exam questions, you've only got, the average exam's 90 minutes usually. For almost every IT exam that I've sat, you've got 90 minutes to get through all the questions, and obviously for most of the exams will be taken, it includes subnetting. Technical interviews, for Cisco I had 2 senior engineers grilled me on subnetting for about an hour, and they were putting up scenarios on the board and I had to answer. I think I had a pen and paper that I could use for working out, but there's no way you can spend a long time doing it. If you're faced with a IP addressing issue, normally what's happened is somebody has manually allocated their own IP address somewhere, because most operating systems like Windows lets you do it. It's left as DHCP, but somebody thinks that they know better and they manually allocate. Alright, so why are we doing all this? I mentioned earlier that when we first had our addresses allocated, there was no thought of home computers or even small businesses. It just wasn't. Computers weren't designed for small businesses, and nobody had any idea that there'd be an internet as we have it today. So it just wasn't designed to do what it's doing today. So a Class A address, you would buy an address from your provider. You would have one network, and you would have, if it's Class A, you obviously have network, host, host, host on your 4 octets, which is, remember, a Class IPv4 address. So you've got 24 bits. 8 plus 8 plus 8 equals 24 binary bits. And if you do the working out, 2 to the power of 24, so 2 times 2, 24 times, gives you over 16 million host addresses. And you've still only got one network. So, I mean, I've mentioned before, but say this is a router, this is the common symbol for a router, and you're going out to the internet somewhere here, but inside you've got your local network with all of your host devices. Now, each interface on the router here can only have one network attached. You can't use 50% on an interface here and 50% here because of the fact that broadcasts are sent out. So before we created VLANs and subnetting, you had to use everything off one network. Class B addresses are better, certainly. You've still got the second 2 octets here for hosts, and the first 2 are for networks. So 16 bits, 2 to the power of 16 gives you over 65,000 host addresses and still one network. So we're in a better situation, but still not great. So I mentioned RFCs a couple of times. Probably worth looking. If you go to rfc-editor.org or just Google RFCs, you can have a look. They're really dry, unfortunately. It's not an exciting thing to read. But have a look. Subnetting has been updated, but it was first proposed in RFC number 950. And you can see in the document there it says updated by whatever, who the authors are. You can do text or PDF here. And then there's a URL if you wanted to share the details with anyone else. So proposed back in 1985. And what it says is you've got the address. Before we just had the IP address. Oh, my writing's awful, sorry. You had the IP address and that was it. Well, this proposed that you add a mask to the IP address and each device will compare one to the other and then come out with a determination. So whatever happens now, because of this proposal, each IP address and each network would be allocated with a default subnet mask. You can't choose not to use them. They all have to be there. And we mentioned before that the Class A is just the first octet is reserved for the network. Class B is network, and then Class C, the first 3 octets, the address, whatever the numbers are. So for Class C, and you remember what the numbers are actually reserved as well for these networks. 192.168.2.100. After a little bit of time, you'd be expected to realize that this part here is the host, and it's a host address on this network here. Now, not that we really need to know, but the computers and network devices like routers, they do something called logical ANDing. And what it does is compares the 0 any of the combinations you could have with these two values, and then it will come to a determination. And anything that isn't a 1 and a 1 must equal a 0. This is how it works out which part of the address is the network and which part is the host. So for example, we've got this Class B address here, and just quickly looking at it to the naked eye, a person may not realize, and certainly network equipment doesn't look at the address in this way, it looks at it this way. And how it works out which part is the network and which part is a host is by doing this logical ANDing here. So you can see that a 1 and a 1 equals a 1, and then next here, the next 1 and 1 is here, and there's one next to it, 1 and a 1 here, 1 and a 1 here, and so on. And we have no more here now, there's no more 1 and 1s. We've got some in these 2 octets here. So this is how it does the determination, and it quickly works out that the network address is 140.179.0.0. Alright, so when we have our network address allocated, we obviously can start adding host bits to it, and the host bits will be attached to, one will be attached to a router interface here, and it'll normally be the first available address, for example 1. Then you'd have a switch, a network switch. Here you could have an IP address. Let's just say we're not adding one at the moment for whatever reason. And then each of our hosts here could be allocated probably by DHCP, but it would be .2, .3, .4, .5, and so on. So I'll just get rid of this, just to make it a bit of clearer. Alright, so we've got host bits here. All these bits here and these 2 octets are hosts. We can't touch these, we can't do anything with these because these are fixed for the network. So this looks like a Class B default address. So what we can do is start adding our addresses. You could say the first host number is 200, but you probably wouldn't start off at 200. You would probably start off saying address 1, and obviously you would put a 1 in the first column here for the binary bit, and then the next address you would say is 2, so you would have a 1 here and a 0 here, because remember we've got 1, 2, 4, 8, 16. This is the binary octet, and you keep going up. Now you could actually, this is where it all starts looking weird, because you could think, well, that doesn't look like a host address. Well, it is. All you've done, remember, all of this is the host. All you've done is turn all the bits off in this last octet. 1, 2, 3, 4, 5, 6, 7, 8. So you've got all the host bits on, but you've still got all these host bits here in octet 3 that are turned off. We haven't used them yet. And then you roll over, so you could carry on counting up. You could have a 1 here and then all zeros here, and keep counting up. And finally we'll get to almost all of the host bits on. I don't know if I've got a graphic for that actually, yeah. So these are all our host bits here. You can see they're all on apart from this very last one. And network equipment, it doesn't care. It doesn't have any thought whatsoever. All it does is look at the logical and or in, and it can see, hang on, all the bits aren't turned on, so it means we can still use this for a host address. And you could allocate this last number 140.179.255.254 to a PC on your network, no problem, because the maths works and you're following the process. Now, some addresses we can't use, and this is where they'll try and catch you out in the exam, or you could be troubleshooting problems in the real world. All host bits have been turned on. So the last 2 octets are for our host. You can see every bit's turned on. This tells the network it's a broadcast. Now, broadcasts are a normal part of IPv4 traffic. It's not something that you would look at on a network and say, oh, that shouldn't be happening. It does happen sometimes, especially, for example, when a PC first boots up, and say you're using DHCP, it actually does send a broadcast packet saying, what is my IP? This is done using broadcast technology, but we'll be using VLANs and switches and other technology in order to stop this propagating through the entire office if you're working in a massive company. Now, this other address here, you can see all host bits are off. Well, this actually has a meaning as well. This is the network. You would use this address for a routing protocol, for example, OS and PF. You would start configuring networks and not host addresses for your routing protocols, or when you're doing some sort of static routing or access lists. You would say everything on this particular network is permitted, denied, or advertised through a routing protocol. You can work out, we're going to be going through this in quite some detail later. This is part of my subnetting cheat chart, and all this is, we've mentioned before, is the powers of 2, where you take the number 2 and double it, double it, double it, double it, double it, double it, and obviously you can count up a long way down here. So the formula to work out your host addresses is 2 to the power of whatever, however many subnet bits we've stolen, and we take away 2. Which 2 are we taking away? The subnet number, or the network address, which is all our bits turned off, and the broadcast, which is all the host bits turned on. Now, you don't need to write this down and remember it, but this is just a representation of how many bits we've stolen. This is for class B, so this is your 3rd octet and 4th octet here for 16 bits. All the bits are turned off, which means it's just the default subnet mask. We've got one network, and each network has got 65,534, which is 2 to the power of 16 minus 2. And then we start stealing bits. This is what this whole course is about, so just bear with me and we'll go into more detail later. We've stolen 1 bit, so if we've taken that 1 bit, we get 2 networks, 2 subnets, and each one, we've got less host bits now. We've got 2 to the power of 15 host bits minus 2. So you can see this is going to go a lower number, and our subnets, as we steal more bits from the host bits, we'll obviously have more networks but fewer hosts. So this number will grow, this number will shrink the more bits we steal. But we'll go into this in more detail later. So what if we stole from the host bits? This is the whole concept of subnetting. We've got 5 bits here, which normally would all be for our host, but we've taken them. We use a different subnet mask value, and we've taken some of these bits, not all of them, but some of them. It looks like there's 5 in total. So we're carving out subnetworks. If we use our powers formula, 2 to the power of 5, that would get us 32 subnets. That leaves 11 bits because there's 16 bits altogether for hosts. That still leaves 11 bits for hosts. 2 to the power 11 minus 2 for the subnet and the broadcast numbers. That gives us 2046 hosts per subnet. This is far more workable than what we had before, which was one network and 65,000 hosts just on that one network. Working out the subnet mask, I'll show you how to do this in a lot more detail. We've stolen 5 bits from the octet number 3, and all we do is add these numbers together. 128 plus 64 plus 32 plus 60 plus 8, that equals 248. We'll use the subnetting cheat chart later that will just give us the answer when we tick boxes. So I've mentioned this before, if the router looks, or PC looks at the bits and they match, if the subnet bits match, then we're in the same subnet. This is why the subnetting is going to be so hard, because we're working all this out in decimal. The network devices are calculating this in binary, and they're doing it very quickly. So this is our 5 bits that we've stolen. If this number matches in another IP address, we're in the same subnet. We have to be because of the maths. So this number here, 129.10, 147.32, 129.10, 148.85, is it in the same subnet? Well, you'd never know by looking at these 2 addresses. You need more information. But the router says, hang on, matches. Next address, 129.10.154.2, is that in the same subnet as these 2? Well, without more information, we don't know. The router says 5 bits, sorry. We've stolen 5 bits. The router says, yep, that's okay, that's okay, that's okay, that's okay. No, that doesn't match because it's a 1 in the other subnets. So what this means is this is in a different subnet to these 2. And what happens is if you're using the same subnet mask, you can't allocate numbers from this subnet into this subnet. It won't work. Alright, so a fair bit of information, but I'm chunking it right down so you don't get overwhelmed, hopefully. Take the quiz and I'll see you on the next presentation. Welcome to VLSM, and I'm going to talk about CIDR also. I know there are a lot of abbreviations to learn, but this is the common vernacular that you're going to have to know when you're working on networks and speaking to other network engineers. Nobody says variable length subnet masking, it just takes too long. So we just say VLSM, and the same with the other terms we use. So this lets you add to the default subnet mask. So I'll just go back a minute. So you know, say we had 255.255.0.0. So this would be our class B. And as we've already seen, we've got host bits here, and VLSM lets us take some of these host bits. So instead of having 16 host bits, what we'll do is we'll take 5 bits to create subnetworks, and then the other 11 bits for hosts. So subnetworks, and this will give us however many we can use, and each one will have however many host numbers, and we'd have to use the power of 2 for that. Previously, say we were allocated a network address by our internet service provider or whoever's in charge of allocating addresses, and they gave us 172.16.4.0. However, this is only one network with however many hosts. I haven't worked it out. But what we've got here is a network here between these two devices, and then we've got hosts off this switch, of which we need 55 here, 12 here. This is a larger LAN. There's 240, and then finally down here we've only got 100 hosts. However, we've only got one network and we can't split it. Well, using VLSM now we can. I'll come into this more detail later, but what this lets you do is chop the address down. So from here you can see from /22 we've stolen some more bits, and this has led us go into this portion of the address. Here we've stolen some more bits. We've got a /28. Here we've got /25. Now there's certain rules you have to follow, and I'll explain those rules to you later, but I just wanted you to see the concept so you could take what was previously one network and create smaller networks. Classless inter-domain routing, we call it CIDR. I have never heard anyone say CIDR, because that obviously refers to the alcoholic, appley tasting drink, which is making me thirsty thinking about it. However, back to CIDR. This was proposed in several RFCs, and there could be others. These are just the ones I know about. What is it? What does it do? All addresses were previously classful. So this is what I mean by classful. It was fixed. 255.0. Fixed. Well, routing protocols originally only supported this format, the fixed network address, because CIDR wasn't invented yet. And then CIDR came out, these RFCs were created, and what it allowed was modern routing protocols to support classless networks. So instead of having the default, you're taking the default address and having, for example, /12 for what would normally be a Class A address. And the modding protocols, I didn't list any here, OSPF, EIGRP, and there's others. So first concept we need to be aware of is slash values. This is, you would never read out this address to another engineer. You would give a slash value. So 8, 16, 24. You would say, oh, that's got a /26 mask. It would sound really odd if you read that out in full to somebody at work. So you represent this address when you're showing it to somebody else, and some equipment will let you just do this as well. It will just let you say /26 instead of writing all this out in full. So the slash basically represents how many masked bits. So this is obviously, it looks like Class C. It could be a Class A, bear in mind. It could be a Class A, but we've added some other bits to the other octets. This was originally, probably originally a Class B, 16. We've taken one bit from the third octet here, and what we would say is this is /17. And this is a common address for point-to-point links, and is 30 binary bits turned on. I'm not counting this, by the way, but these 30 binary bits altogether, and that only leaves 2 bits at the end for hosts. The other concept that CIDR permitted was something called supernetting. This goes by different names. It could be called route summarization or route aggregation, and it's putting a group of networks together. Say you own all these networks, it puts them all together and you send out one network address out to the internet. What this does is save on CPU and it saves on bandwidth. Because what people don't realize is if you add a protocol to your network and say it's 100 meg link, 25% roughly of this bandwidth is immediately reserved for routing updates. So you've lost this amount of bandwidth for all the updates to be sent. So what you can do is you can use route aggregation, and say you've got a large number of networks, you can advertise out a summary. So this is a 24-bit mask. You can see it's got /24 binary bits here in the subnet mask, and what we've got is a few networks that it could be hundreds. I'm just doing a demonstration. We own all these networks, and what supernetting lets us do is count how many bits match. So 8 bits, 8 bits, 8 bits. These bits match on the third octet. So there's 5 bits match, 5 bits match, 5 bits and 5 bits. So basically 8 bits here, 16 plus 5 gives you 20, 60, 17, 18, 19, 20, 22. 6 bits, isn't it? Sorry, that's why I was getting confused. 16 plus 6 is 22. So you've got 22 bits that match. However, the default mask is 24 bits. So what supernetting lets you do with CIDR is say, I own all of these networks, but I'm going to advertise a summary route. And that summary route represents all of these networks because the binary math works, and you would take the lowest network number and advertise the mask that we've worked out by comparing the ones and the zeros to see what matches and what doesn't match. I think I'll be covering this later, but I just wanted to explain the concept of two of the concepts that we're going to be covering in more detail later. So that's all for now. I'll see you on the next presentation. Route summarization and VLSM. Two other important topics for the CCNA exam, and you can be sure you'll be tested on them in one way or another. So you'll be asked to do some sort of summarization or design, and I'll show you what they are and how to answer the questions in the exam. This is another one of those lectures where you'll probably need to go over a few times until you're happy that it's actually sunk in, and then try some examples for yourself. So imagine working in a large enterprise network and having hundreds of internal networks. Each one has to be advertised, obviously, so the entire network is aware of all the other networks, and they have to be stored in routing tables. Now this is actually quite a small example. I've got 1, 2, 3, 4, 5, 6 routers, all with various size networks off them, various internet interfaces, for example, Ethernet going off to subnets or whatever. Then they advertise their tables to each router, and eventually all these routes go off to the internet. So this is a lot of traffic being sent to and from and in and out, and it all's taking up bandwidth and CPU cycles. So route summarization allows us to aggregate all of the routes into as few as possible, and there's a technique to doing it. For example, look here, imagine if we could, from each network or group of subnets, we could chop it down just to one summary, and that summary points any other router towards the home router where it can actually allocate it to the correct subnet. So there is a way of doing this if we apply route summarization. The important thing is from the very outset to plan all of our addressing, and we saw it earlier when we were dividing our subnets up. And so many times when you go to companies, I mean, sometimes they've bought out of the companies or just grown exponentially, or it hasn't been well thought out, and you couldn't particularly blame a person for it. But a lot of the time, you can, with careful planning, you can make the whole process a lot easier. And it's important to get into good habits when we're at CCNA level. So firstly, the routes must be contiguous. That means you don't split them up. You don't put one address on this side of the network, then jump to 172.20 another side, then 172.16.4 somewhere else. It's all just a mess, and it doesn't lend itself to be summarized. So just a repeat of the other diagram there. So how to summarize? We find the matching binary bit. So this is the technique, and then you find the lowest network or subnet number. And then we match the binary bits, to the lowest network subnet number. Now this won't make sense until we actually look at some examples. So we'll look at a tiny portion of this network we were looking at a second ago. And you can see we've got 4 subnets, 172.16.20, 21, 22 and 23. So we've got 4 routes that really should be advertised from that router. And for whatever reason, this has been built with a 24-bit mask. So all we do is underline all of the matching bits, and you can see we've done that. We've got all the way across as far as the first 22 bits, and the last octet is they're all agreeing that the last octet, the third octet there, is 000101. After that, the values are all changing. So what this means is we can match the first 22 bits, look at the lowest subnet number and advertise that. And that literally is all there is to it, as far as it goes for the exam at least. So what we could do is say, okay, we've got 22 matching bits, our lowest subnet is this, 20.0, and advertise that. As I said, that is it. Now let's look at a larger set of subnets that are going off the Ethernet interfaces or whatever on router A. So we've got 24 all the way up to 31, and there was a 24-bit mask applied. So let's shrink it back, and we've found, if we count 16, 17, 18, 19, 20, we've got 21 matching bits. After that, all the bits are changing, as you can see. 000, 001, 010, etc. So let's take our lowest subnet here, which is 172.16.24.0, and we can take however many bits we've got matching, and we've got 21 here. So we can advertise that summary route from this router. Now it's time for you to stop the video, no cheating, and work the rest out. And eventually we'll be able to get to router F and do the whole process again and summarize even further possibly. Alright, so here's my answer. I hope you got the same answer as me. Just for the final route that's going out router F, you just take the lowest possible subnet value. So we couldn't advertise 172.16.0.0 because that network 16.0 and anything below 172.16.16.0 may be somewhere else. And bear in mind the actual routes you may be advertising are routable routes that people have bought and paid for. This is why you should be very careful. But say you're sending this out to another side of your company on a VPN or whatever. So this is why you can't reduce it any further than the lowest subnet you've actually got in use. VLSM, these sort of subjects but together. The old rules, if you remember, meant that you had to keep your subnet mask fixed. So VLSM allows you to chop your subnet into mixed sizes. And each different size subnet can be allocated. So you could chop down your subnet and have some smaller sizes, medium sizes, larger sizes, as long as you comply with all of the rules. So without VLSM, we've got something crazy here. We've got two networks, one on either side of each router with a /28 mask, and looks like we're counting up in increments of 16 here if my memory serves me correctly. But then we've got a point-to-point link between the two routers that only needs 2 host addresses, and instead we've subnetted it in such a way that it's got 14 available host addresses, which is just a silly waste. So VLSM lets us keep this nice and tidy and tight. Alright, so let's move on. We've done something a little bit smarter here, and we've got a /30 mask for our point-to-point links. And we'll look at how to do this. So expanding the network with VLSM. This is an example here. We've got a point-to-point mask for our point-to-point links, and we've got our /28 masks for various LANs that are sitting off the back of the routers. I know I've only got one PC there, but it's just to illustrate our local area network. Again, it needs to be carefully planned, because if your addressing is all messy, then it just isn't going to work. So let's look at a case study. We've got 3 point-to-point links, and we've got 4 networks. One's got 100 hosts, the others have got 20, 20 and 25. So we need to be a little bit smart here and work out what to do with our 200.100.100.0 address. And this is a sort of question you'll have in the exam. So with practice you should be able to do it quicker. So at the moment we've got one network, one subnet with 254 hosts, which simply won't do because we haven't even got one network. We've got 1, 2, 3, 4, 5, 6, 7 networks. So we'll need 7 subnets. Host numbers range anything from 2 hosts for point-to-point all the way up to 100. So we'll go back to the subnetting cheat sheet which we used for fast subnetting. Which mask will give us 100 hosts? Well, we don't have to work it out in our head. All we do is tick down in the host column 7 places here. 1, 2, 3, 4, 5, 6, 7. 64 won't be enough, so we've got to go to the next available number, which is 128. If we've taken 7 bits for hosts out of 8, that only leaves us 1 bit for subnets. But this is okay, because remember we can chop our network into smaller and smaller pieces, so we're going to be okay if you just follow along with me. So that's going to give us 126 available hosts if we take 2 away and 2 subnets. Now we stole 1 bit for subnets, so if you went to the upper part of the chart, I've chopped the chart into pieces here, but if you take the upper part of the chart, you'll see that we'd steal 1 bit, so that gives us a mask of 128, and it gives us an increment of 128. So these are our 2 networks at the moment with what we've done. One of these 2 subnets now we're going to have to chop down into smaller pieces. So let's take the higher subnet and use that for our lower LAN host that needs 100 hosts. We've got 126 I think we said, but that still leaves us with 1 available subnet and 200.100.100.0. We've still from this value got to create 3 local area networks and 3 wide area network links. So I've ticked across 3 places there to give us an increment of 32, and the working out behind this, you can see here we've got 6. We need 6 subnets, and the closest I can get if I tick down the subnets column is 8. 4's no good, so I just have to tick the next one and steal 3 bits, and that leaves us 1, 2, 3, 4, 5 bits for hosts. 32 minus 2 is 30, so that's fine. That will match all of our LAN hosts, and it will give us enough subnets. I actually knew it was going to work all along because I worked it out back to front. So if I've stolen 3 subnet bits, I tick down 3 subnet bits to give me the increment of 224. So where are we now? If we tick down 3 places or still steal 3 bits, we can use a mask of 27. So because our 24 mask plus 3 is 27. So we can break this down. We're counting up in increments of 32, and we can do 0, 32, 64 and 96. we can go all the way up to whatever our subnet value is, which is 224. So the first network, the 0 subnet, let's reserve that. Let's put that to one side and keep it for our WAN host. You could have chosen any subnet, but I'm just going to choose the first one there. And that gives us our other subnets, each with 30 hosts, I think we said, the .32, the .64 and the .96. Oh, it's worth bearing in mind, it's probably obvious, but you can only use the IP address once. No matter what the subnet mask is, the IP address can only be used once. So here's what we have so far written out and allocated to different parts of our network. So the last bit is taking care of our wide area network hosts. We need 2 hosts, so if you tick down the host column, 2 is no good because 2 minus 2 is 0. So 4 minus 2 is 2 hosts per subnet. If we steal 2 bits, that leaves us with 6. So we tick down, that gives us 64 subnets, each with 2 hosts. Well, we actually only need 3 for our wide area network links. And then if we tick down the same amount in our subnet columns, it gives us 252 as the subnet mask. And our increments will be going up in 2. So, sorry, our increments are going up in 4, as you can see. So if you look at the first 3 addresses we have, our subnets are 0, 4, 8, all the way up, 0, 4, 8, 12, 16, etc. We've only got 2 host addresses per subnet. So our first host address will be 1, our second host address will be 2 for the first WAN link, our broadcaster will be 3, 4 will be our next subnet, 5 and 6 our next host, 7 our broadcast on that subnet, etc. So this is the whole thing now spelled out for you. You could have used different subnets for different parts as long as you follow along with the principles that I've outlined here. So hopefully this made sense. Again, like the other subnetting lectures, go through it quite a few times, work it out in your head, work it out on pen and paper using the cheat chart, and then start creating your own examples. This is the final result all written out for you. Thanks for watching. I just wanted to touch on a concept which we're going to go into a lot more detail in the coming presentations, but just to get our head around what's happening and why it's happening. So given an address and a mask, how many subnets and then hosts per subnet are generated? So this is your typical exam question. And say, for example, we've got, we were given a class B. I didn't specify this, but say this is a class B, and normally, as we know, this would be 16 binary bits for the mask, but we've got another number here. Instead of the 0, 224 has been added. So we're obviously doing some subnetting here. So what we've got is the first 3 binary places in our octet spoken for, which is the 128, the 64 and the 32, which we've got a quicker way of adding all this up in a while, but it's basically 224. So our mask, this is why our mask here on the 3rd octet says 224. So we've got 16 bits that were originally for the network. These are our subnet bits now, but we've still got a lot of host bits available. So each subnet will have a lot of hosts available. Now, if this subnet here, you could have as many values as you wish with these 3 places, the 64 and the 32. So these are all the possible combinations of 1s and 0s if you put them together. So 1, 2, 3, 4, 5, 6, 7, 8. And again, this is the super duper long way of working it out. You wouldn't do this in an exam. So we've got 8 subnets if we take 3 bits from this third octet. Alright, so we've got our 224 mask, and I've written it all out in binary to make it quite long-winded. And we've got our network, our subnet, as I've said, and our hosts. So this gives us all of the values which we mentioned, 001, 010, etc. We know there's 8. So this gives us 8 subnets. Or if we just work out these 3 bits here, and it's 2 to the power of 3, sorry, this should be superscript, 2 to the power of 3, which means 2 times 2 times 2 gives us 8. And we'll go through the powers of 2 column later when we use our subnetting cheat chart. This leaves 13 bits for our hosts over here, and 2, again, it should be to the power of, sorry, I didn't check that, 2 to the power of 13. We take 2 away, 1 for the broadcast and 1 for the subnet. That gives us 8190 hosts per subnet. Don't get caught out in the exam, because this is every subnet has this many hosts. It isn't just in total, but each of the 8 subnets. So we'll go through the host addresses and broadcast for the below subnet. So as you know, each subnet will have an address that we would use for example, a routing protocol. We've got our subnet mask, and these are all the possible values. So this is like an exam question, if you like. You're given 131.107.32.0 with this mask. What's the subnet address? All your host bits are 0. What is the which matches here? Sorry, the first host, you'll add a 1. So this is the binary. This is the decimal. You'll add a 1, then a 2, then a 3, and you will keep adding bits. I always recommend you add numbers from 1, 2, 3 onwards, and you'll be using probably a DHCP service, which will probably do this automatically. So what you can do, you can keep on counting, keep on counting, keep on counting until, and we've talked about this before, almost all of our host bits are turned on. There's just one host bit here which isn't on yet. And if we turn that last host bit on, as we know, this is now a broadcast on the subnet. So if you wanted to send a packet to every single device on the 131.107.32.0 network, to all devices, it would be this address here, 131.107.63.255, and this will be a typical exam question, and you'll have obviously different options, the correct one and then the wrong one, .3.11, whatever. These will all be incorrect, but because I'll show you how to work all of this out, you'll be able to quickly see, yeah, that's the answer. So all of these numbers, I think we said there was over 8,000, sorry, 8,000 plus, you can allocate to hosts, no problem, and you can do it in any. Does my pen stop working? Welcome to the shortcut method. Just to emphasize, this is not how you're going to be answering questions in the exam. This is a kind of intermediate step. So I suppose step 1, working everything out in binary. There's this method here, shortcut, and then easy subnetting. I didn't make my box big enough. So this is the exam method, which we'll be covering later, but you could actually learn this way. But if anyone ever asked you in an interview, or how did you answer that question, or if a customer says, why can't we use this particular network address or broadcast address, if you don't know this way and then this way, you're just going to look a bit silly. So this method here that I'm covering is the intermediate solution. This is not using binary, but it's still kind of too long for exams. Now, just bear in mind that when you go on YouTube or you buy almost any IT book, so like the big name publishers, who I won't mention their names, but the CCNA and Network Plus, etc., they're all teaching using this method. The problem with this is, as I said, it just takes too long in the exam, and it can be also a bit confusing. But we'll go through it so you can just see why the easy subnetting method is the best to use for the exam. Now, these are the steps to answer any question, and the major flaw is for some of the questions they might only ask you one thing, like how many hosts per subnet, but you've got to go through all these steps in order to determine the answer. So going through all of this way could take you maybe 5 minutes. The easy way is, I'd say after some practice, about 60 seconds, could be even less. And this is only because you're practicing this method quite a few times. So the first step here is how many subnets. You go 2 to the power of mass bits. So if we've got 192 in a subnet where it should be 0, hopefully by now you'll know that we've stolen 2 bits, the 128 bit plus the 64 bit, so the first 2 bits, that gets you 192. How many hosts per subnet? Well, how many unmasked bits are left? And then -2. So if you've got 6 bits left for hosts, you go 2 to the power of 6 -2. What are the valid subnets? 256, take away the rightmost non-zero subnet. So if you go 255.255.255.192, so the rightmost non-zero subnet, so there's no zeros anywhere here, so 192, 256 take away 192, and these would be the valid subnets. So what would this be? Yeah, that'd be 64. So your subnet increment would be 64. So your first subnet would end in 0 in the last octet, then 64, then 128, and then 192. We'll do lots of examples, so just stick with me for now. What are the valid hosts per subnet? So the host numbers are any number after the subnet number. So the first number would be 1, or for example, all the way up to 254, and then the final number for the broadcast would be 255. This is why there's 2 numbers we can't use. And then what is the broadcast number? It'll be the last number available on the subnet. So you can answer questions this way, and this is how I used to do it in the exam, but it just takes up valuable time. If you say you get 5 times questions, and each one in the exam takes you 5 minutes, so you're taking 25 minutes to answer subnetting questions, and it's quite common to get 5 subnetting questions in any networking exam, as opposed to this method here, which is 5 minutes. So basically you've got a whole bunch of time there to answer all the other stuff, go through practical hands-on exercises. Some of the exams let you go back and review all of your questions from the start again. You can tick a little box and say mark this and I'll check it later, or even just finish early, whatever. But you just see how much extra time you get, and it's very precious in the exam, especially because you're spending a lot of money. I think at the moment the Network Plus is around $350. It's just really expensive. So let's get an example anyway. Which subnet, so this looks like a host number, 131.107.32.1. Which subnet is this hosting? And the subnet mask is 255.255.224.0. So what's happened? Well, the default mask for a Class B address would stop here and it should be 0.0. We've stolen some bits. How many bits have we stolen? Well, in the third octet, we've taken 3 bits. There's a quick way of doing this, but we haven't done that yet. So basically the 128-bit, the 64-bit, and the 32-bit. Add those together and the answer will come to 224, and then we haven't stolen any bits from the 4th octet, so that's going to be 0. So these are the steps I mentioned earlier. Step 1, how many subnets does that mask give us? We've stolen 3 bits from the first octet, so 2 to the power of 3, 2 times 2 times 2, 2 times 2 is 4, 2 times 4 is 8. We have 8 subnets. That was the answer. How many stolen bits to the power of 2 gives you how many subnets. Step 2, each of our subnets has got, oh, what's happened to my pointer? Each of these subnets has got a certain amount of hosts. We've got 13 bits for our hosts from subnet 3 going into subnet 4. So 2 to the power of 13, this is where you've basically got to write out a chart. 2, 4, 8, 16, 32, 64. You've got to keep going all the way down. And in the exam, unfortunately, you'll get a board that you can write on with a little marker pen, and this is where you write it. But if you did 2 to the power of 3 minus 2, you would find that you've got 8190 hosts per subnet. Step 3, what are the valid subnets? Well, this is an interesting one. We've got our rightmost non-zero subnet, and we take that number away from 256. So our subnet value is 32. So what that means is our subnets will always be an increment of 32. So it couldn't be like 32, 48, for example, because it's not an increment of 32. And you're allowed to start off at 0. This is called the 0. Now, the reason why I mentioned the 0 subnet is we never used to be allowed to use this right up until, what would I say, the late, maybe 2010. And before that, if you tried to input the network address, the first available subnet of 0, it would throw an error and you couldn't use it. And you couldn't use the last subnet value, which is 224. Basically, it was a recommendation as a result of an RFC, and it blocked out 2 of your subnets. So instead of having 8 subnets, you only had 6 to use. Well, Cisco have changed their code, whatever version it was, 12.13 or whatever, I'm guessing now. Now you can use it. So this is basically giving you a lot more flexibility, and it's recognised. I only say that if you've been studying from an old book or you've been in IT for a number of years and you think this still applies. This is really the reason why I've rewritten my entire book and re-recorded the course. Alright, so we know we've got 8 valid subnets, and each subnet will be an increment of 32. We can start at 0. So the first for the first subnet, so 0, 32, and we're going to count up in increments of 32. And you find if you added all these together, you would have, let's do it in fact. Find my pen again. 1, 2, 3, 4, 5, 6, 7, 8 subnets, each starting with this value of which you can't attach to a host because it's the subnet value, which we covered earlier. Alright, if you get this adding up wrong, if you get this bit wrong here, and if you add up in the wrong increment, say you get confused and start adding up in increments of 16, everything will be wrong. So you must get it right. Step 4, what are the valid hosts per subnet? Well, let's look at our first subnet, 131.107.0. You can add any number except the broadcast, and you can't go past the subnet. So you can't start using subnet 2's numbers. That's a different subnet. So any number after 1 and not including the broadcast, but earlier than that, you can use. And remember I said, okay, let's start counting from the number 1, the first available number. Alright, I've listed the subnets here. So let's have a look. Subnet 1, you know, is 00 in the second 2 octets. You know the next subnet is 32.0. So it stands to reason you can't use this address. You can't use this address. To work out the broadcast, we take 1 away from the next subnet. So 32.0. 131.107.32.0. If you rewind one number, which would be 31.255 in the second, this is octet 3 and this is octet 4, this would be our broadcast. So it stands to reason that our first host will be 0.1 and our last host number will be 31.254. Or if you want me to write it out in full, 131.107.0.0 subnet 131.107.0.1 host 1, and obviously there's 8,000, so I'm not going to write them all. You jump forward to the broadcast, which taking away 1 from the next subnet, 131.107.31.255, take 1 away from that to get our last host. 254. Again, just follow along with me because we're going to be covering a lot of these examples. So what is the broadcast address? I already mentioned it actually. You take whatever the subnet is here and you take 1 away. And remember, we are working in binary, so you wouldn't just go 31 or any other permutation. You have to take each value of each octet. First to 2 are the network, and then our subnet and hosts. So you have to rewind by 1, and if you rewound 0 by 1 in this column here, which can go from everything up to 255, if you rewind it back again, it goes 255, 254, 253, and so on. So that's enough for now. We're going to be covering more examples. I just wanted to start showing you the sort of intermediate way of working out subnetting. I'll see you on the next presentation. Welcome to our next example. We're going to be doing this the kind of intermediate speed way, so don't worry too much thinking, oh, it takes too long, or why are we doing it this way. This is just our middle step. So this was the hard way, this is the kind of intermediate way, and then we'll move on to the easy way, and we'll be doing loads of examples. I can't remember actually, I think it's about 25 examples, and then at the end I'm going to point you towards other resources you can use to get even more subnetting hands-on practice. But you only really need to do it once, so you spend, say, maybe 2 weeks on this, and then I'd say every month, just 1 hour, just jump onto a subnetting practice website, or do some subnetting practice exams, or make your own examples up just to refresh. And then anything you're not sure of, go back to this course, and then go back to doing your 1 hour a month. And I know when I came to update this course, I just had to brush up on a few things, and a couple of things had changed since I wrote the book. The 0 subnet had changed, and just a couple of other small things. And obviously we've got IPv6's really prevalent now. So back to the question, which subnet is this hosting? 10.20.1.23, and we've got this subnet mask. It should be 255 with 8 bits, but it looks like we've stolen some bits from our second octet, and obviously it's only the first octet which is used normally. This is normally all for hosts. So we've carved a few subnets from our host portion. It still leaves 8 in this subnet, 8 in this subnet, and however many in this subnet. So 240 in binary is 4 ones in the first 4 columns, or you've turned on the 128, the 64, the 32, and the 16 bits. If you add all those together, you will get 240. I know because I've done this so many times that if I see 240 or if I see 4 bits are taken, I know that it's going to be that mask, only because I've done this loads of times. How many subnets? We've stolen 4 bits. So 2 to the power of 4 equals 16, or if you wrote a powers of 2 chart, 2, 4, 8, 16, 1, 2, 3, 4. So we've got 16 subnets. We don't take anything away from this number because subnets are an absolute value. It's the host that we have to take 2 away from. Speaking of which, how many hosts per subnet? We've got 20 bits left for hosts. In the exam, I doubt very much whether they're going to get you doing this 2, 4, 8, 16, 32, 64, up to a million, however many. It's like I said, how many bits down? We're 20 values down. It would be a bit unfair, to be honest, because you're spending all your time working out powers of 2 instead of how to answer subnetting questions. But anyway, we'll get the subnetting cheat chart later on. 2 to the power of 20 minus 2 gives you 1,048,574 hosts per subnet. Far too many normally than we'd need. What are the valid subnets? 240 is the rightmost non-zero subnet. So we take 240 away from 256 to get our subnet increment, and remember we're allowed to start off with subnet 0, and then it will be 16, and we'll keep counting up. Don't make a mistake here. Don't go 32, 64. In the panic in the exam, you can just look and think, oh, this number's double that number, and in your head it jumps a step, when really you should have kept adding 16. It's I say this because I've done it myself, even when I was writing the books. Luckily, I've got a load of copy editors. I've got a another book, which by the time you're watching this is out, 101 Labs. You can check on Amazon for this. I'll try and get a graphic later if the book's ready in time. 101 Labs IP Subnetting. And I'm writing all these labs, 101 obviously, and I've made this mistake a couple of times, just getting excited or tired for whatever. So what are your valid subnets going back? We're counting up in this second octet where we stole our bits from. So 10.0, 10.16, 10.32, 10.48. And remember, the question is asking where's this host? Well, it can't be in this subnet because it's too low, and it can't be in this subnet because it's too high. This sounds like Goldilocks and the Three Bears, doesn't it? Oh dear. So you've answered the question in the exam, and I'll cover this again later. Once you get the question, tick the box and move on. Click the next button. Yeah, but I'm just showing you how to work the whole thing out. So anyway, 32, 48. Unfortunately, there's a lot of subnets, so I'm going to stop. But you would end up with 224 and then 240. You can't go past number 240. The reason being, this is your subnet value, and you'll always find that this is your last subnet. Is the last value in the subnet mask. What are the valid hosts? On our first subnet, it's 10.0.0.0. So you start off counting number 1, and you go all the way up to the last number, but the last binary bit will be a 0. That's easy to recognise on this subnet. On the next subnet, it's obviously harder to recognise because we're not using all zeros here. Our host is in here still. which we found that on the last slide. These are all our host numbers. You work out the host numbers by basically finding the next subnet, and then you take one away. So it'd be 10.47.255.255 to get the broadcast. Take one away from the broadcast, and that gets you your last host number. What are the broadcast addresses, which I've already mentioned? The last host on the first subnet, and then that's the broadcast. I got this by basically going to the next subnet and taking one away. The 32 subnet, I took one away from that and I got the broadcast address. And the same, basically. This is exactly what you do. So you can get the subnet answer and you can get the first host. You can't do this next. You can't do the last host. You've got to basically jump forward to the broadcast and then go back to the last host. And then you'll have all 4 bits of information that you'd need for any exam. Alright, so I think we're at the end. Thanks for watching. We've got lots more examples coming up. So I just wanted to cover the type of questions you're likely to face in the exam. Most any networking exam or technical interview, to be honest. This is the most common sort. Which subnet is host, and then they'll give you a number. So which subnet is host, whatever in, or which hosts are in subnet X. What is the broadcast address of subnet X? So say we have something easy, 192.168.1.0/24. You'd be expected to work out, you've got the subnet, so the first host, last host, and broadcast address, and obviously which hosts are in this subnet. And what you'll probably have is several answers, if it's multiple choice, and you'll have to tick which ones belong in that particular subnet. It could be a single choice, or you could have multiple choices of numbers in this subnet. Obviously, the broadcast address we've covered, and then the hosts. So it could be multiple hosts, as I said, and just one host. That's the most common question you'll have. Next is what I call the design question. And we've already answered both types really, although we did it in a long-winded way. How many subnets and hosts per subnet? So it'll say something like okay, I'll just use this example again. So this time it's a /26. How many subnets are generated from this mask with this type of network? And then how many hosts do we have per subnet? And normally if you've got the default mask, there's obviously just one network. So they're the 2 types of questions. We're going to be spending a lot of time on these 2 types all the way through the rest of the course. I don't know how long it'll take, another couple of hours to go through all of this. And then we'll be using a kind of easier way to answer the questions. So typical question pops up. You've got the exam testing software, which subnet is host 192.168.21.41/28 in. So we know we're doing some subnetting here. Now the first task is to change the 28 mask to a full subnet mask. I say this, you don't actually have to do it if you already know that it's a class C address, which it is. If you already know that it's /24 by default and it's now /28, you already know that it's had 4 added to it. So when I say change the subnet mask, to longhand, then you'd put 240 on the end instead of 0. but really what we're trying to get to is the fact that we've stolen 4 bits for the subnet mask, and these will be obviously in all those combinations we mentioned. So 0, 0, 0, 1, 0, 0, 1, 0. Obviously working it out this way would just be torture, so we're not going to do it that way. Now with 4 bits of masking we have 24 equals 16 subnets. I put 24 equals 16. So if we go 2, 4, 8, 16 in the powers of 2, we've got 16 subnets. This leaves 4 bits for the host, which is 24 minus 2. I'm not sure why I'm saying this. I'll have to check into that, sorry. It's 4 to the power of 2 minus 2. So that gives you, I think what's happened is I've pasted it in and it's ruined the formatting from the book. So 2 to the power of 4 minus 2, that gives you, it would give you 16, but you've got to take 2 away. So 14 hosts per subnet. So I'm giving you the design answer here also, so I'm answering the other type of questions, but we're going to go into now working out the which subnet this particular host is in. So subnet mask is 255, 255, 255, 240. We've got 4 mask bits. Now we know the last part is 240, the last part of the subnet mask. So it's 240, take it away from 256. This gives you the increment, which is 16. So our subnets will go 0, 16, 32, 48, and so on. Alright, so all we have to do now is count up in increments of 16 until we get to the subnet that the host number, because we're subnetting on the last octet, is in. Alright, this is what's known as the 0 subnet, the very first one. The next one will be an increment of 16. We're still looking for this number here, 41. So it's not going to be in here. 32, more likely it's going to be in here. And I've actually put that the answer, it is in here. I've worked out the broadcast again by taking the next subnet and just minus 1. And then the last host, you take away 1 from that. So I've got the answer. I think I've put all the subnets in here, or some of them. Yeah, almost all of the subnets. I just didn't have room because there's 16 altogether. So the answer is, which subnet is that host? 192.168.21.41 in. It is in 192.168.21.32. Which subnet is host 1065.25 in /10? So we'll turn the 10 into a subnet mask. I remember why we're doing this now. I said we don't need to do it. If we're doing it the Longcad way, you've actually got to work out what this number is to take away from 256. I haven't done it this long way for so long. I'd actually forgot that, so it was remiss of me, sorry. So we've taken 2 bits, which is the 192 bit and the 128 plus the 64. So that's going to be 192.0.0. And we've obviously got 2 binary bits stolen in this second octet. 2 to the power of 2, again I'm really sorry about this, 2 to the power of 2 is 4 subnets. That leaves 22 bits. So you've got bits in this octet, 6, you've got 8 bits in this octet and 8 bits in this octet, all 4 hosts. Now that gives you an awful lot of hosts, over 4 million hosts per subnet. What we're most interested in for this type of question, I'm sort of giving you how many hosts per subnet design, but what we're most interested in is the subnetting type of question here. But doing it this Longcad way, you get all the answers to all of the questions. So 192 away from 256 gives you the subnet increment, and as I keep telling you, you can start off at 64 and keep going from there. We'll only have 4 subnets, so I'll write out all 4. You have to stop on the 4th one, even though we know there's 4. You have to stop at 192 because this is the subnet mask. Whichever octet this final mask is in is where we stop, because we've run out of bits. Alright, so we'll count them on our subnets: 10.000, 10.6400, 10.128.0.0. You can obviously stop here because the answer's in this second subnet, and then the last possible one. If you wanted to work out the hosts, basically the first number after, so the first number after 6400, 6401, then you jump forward to the next subnet, 10.128.0.0. You take 1 away, which will give you 10.127.255.254. Sorry, 255, and then you take 1 away to get the last host number, which will be 10.127.255.254. Alright, we're still doing it the kind of long-ish way, and we're getting answers to questions that haven't been asked, because this is how this particular system works. We're getting through the design bit, and then we're getting to answer the subnetting questions. And you can see each question, although I'm having to do a commentary, which would take me longer, if I was doing it in the exam, it would probably take around 2 minutes. That's because I'm experienced. The average person, you give it 5 minutes maybe. So, the reason is producing the answers to all of the questions that you could be asked, but also it's showing you how all of this works before we go the easy subnetting way, which just skips straight to the answer. Alright, so we've come to the end. We're going to go through the subnetting cheat chart next. I'll show you what it is and how the various parts of it work. So welcome to our section on the subnetting cheat chart. I used to call this in my other book the subnetting secrets chart. It really doesn't matter what you call it. I kind of came across this method when I was working out subnetting, had to teach subnetting back in 2002. I haven't seen this anywhere. I've seen people kind of try to teach this but without a chart, and try to use various easy subnetting methods to show you, and these videos end up hours long, and I don't really think they help. For the exam, I should be able to write down here, you need something that's fast, accurate, consistent. What I mean is it works whether you're going to get a class A, B, a C, or design questions. And this is where it all falls apart. Somebody will show you something that works with class C addresses, but when you're using 2 octets for hosts or 3 octets, or you're using a class A address but with what would normally be a class C type subnet mask, it all falls apart. Or if the question includes or is only about design, i.e. how many subnets, how many hosts per subnet, they can't answer it with their method. So fast, accurate, consistent, and also has to be easy, because in the exam you're going to get nervous. We all do. Nervous because you might fail, obviously, and look silly, and nervous because you've just probably spent in the region of $250 to $300, plus your travel costs, like your car park costs and train and all this kind of stuff. And some people have to travel a long way to find the testing centre. So this is the only thing I've found that works consistently, doing all these things here, and it's been tested now for 18 years, almost 16 years. And the other thing is, in an exam, you are given normally a whiteboard and a little marker pen, and I think a little scrubber to wipe it clean. And what you can do is, sorry, this thing isn't very accurate. So you can actually write this chart out in the exam. you can copy it out, and then whenever you've written things in here, you can just rub out the answer and just carry on using the chart. So this here, I'll go into more detail in a minute. These are the bits. How you write them is, this is 1 octet here. So this is 8 binary bits. So you would start off, in fact you could start off this side, start off with the number 1 and keep doubling that number in each box. And magically we get to the last number of our octet, which is 128. Now what you will do is you will take this very first number here and put it in this box here under the subnets. 128 plus 64, 192, plus 32, 224, plus 16, 240, plus 8, 248, plus 4, 252, plus 2, 254, plus 1, 255. So these numbers you will recognise as possible values in a subnet mask. It will normally be something like 255, 255, 255 dot 240 or 224 or whatever. These are the only possible values because, as I said before, we're filling in contiguous bits. Say for example here. The powers of 2 is just what it says here. We fill in these boxes here, and say you start off with the number 2 and just double it. 2, 4, 8, 16, 32. Now I've kind of run out of space on this sheet, but you would keep ticking down all these values, and you would get an answer. I'll come to an example in a minute. So the other thing is, this is my method, and it is available for anyone to use, including you. Now this isn't the only subnetting method. This is the only one I know that does all this, but I've done videos before and put them on YouTube, and I've had comments on my Amazon subnetting books, and people have said, oh, I don't do it this way, I'll do it the other way. Listen, you do whatever works for you in the exam, and if you've got another way of doing it, then please use your method. If you can do all of these things and you can remember how to use it in the exam and it works on a whiteboard, then use that. But this is just the method I found that it works consistently, and I've taught this to thousands of people who've used it too. However, like I said, if you want to find a different way of doing it, please be my guest. So just breaking down the various parts. This is the subnets column which I refer to in the video, and you'll be ticking down the various parts until you find the correct subnet number. This is the octet. Now, as you can see, this is only 1 octet. So what would happen is, for example, 192.168.10. And then we're doing subnetting here because this is a class C. So this octet here would be represented by this part of the chart here. Now obviously if we're doing a class B address, there's a slight difference. We need to say we've got 8 bits here, and then this is our last octet or third octet or whatever, but we'll come to that, and you'll be putting ticks into these boxes in our examples. And then the powers of 2, as I said, will be ticking down here. You'll put the number 2, so that's 2 to the power of 1, that's 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, etc. But all I've done to make things easier, 2, 4, 8, 16, 32, etc, etc. That could go down to obviously millions, which there's no point in the exam. I'll tend to go down to sort of maybe this value here or anywhere around here, and then if they ask questions, I'll just keep adding. So if they had me adding more bits, I'll just add them down here. So let's do our very first example using this chart. and I'll keep it simple. So which subnet is 192.168.100.203 in? Well, the first thing we know is from reading our theory books that this is a Class C network. These bits are all network bits. This are the host bits, and these are the bits that we can steal. Now, we've got a /27 address. They could have written it out in full, but they didn't. So I'm preparing you for these CIDR type questions. So we know that a Class C is always /24 by default. And what's happened is we've done some subnetting, and it is now 27. So to get from 24 to 27, all we do is add 3. So this is very simple mental arithmetic. We don't need to use the chart for this. To get from the default /24 to 27, we add 3. So what we'll do is we'll go over here, and the very first thing we do is we tick down 3 places. Behind this chart, if I had some special reveal curtain, then it'll be in binary. We don't really want to be doing this in the exam. I've ticked down 3 places to reveal, as if by magic, the last octet, the value of 224. 3 bits have been stolen. So in order, this is the very last octet. So what this is this octet here. 3 bits have been stolen for subnetting. So I tick across 3. This gives us the increment that our subnets go up in. So our subnets, now we know 2 things. We know our subnet mask, and we know the increment. We know that we can count up in values of 32, and we can start off at 0. 100.0. And we're going to count up in increments of 32. I would normally jump because it's a high number. So 192.168.100, you can't jump from 0.32. I would jump from here, but I won't for this example. Everything's the same, .64. First 3 octets the same, 96. 1, 2, 8. Add 32 is 160. 192. I think that's probably the subnet we're subnetting in, or the octet we should be in. 224 if I had 32. Alright, so I did it the long way. What I probably would have done maybe is just jump from 32 to 96. Depends how good your addition is. So anyway, our host up here, 192.168.100.203, is in subnet 192.168.100.192. If they asked us, you know that our first host would be 193, our broadcast would be 223, and our last host would be 222. So these are the available host numbers. So the answer is, for the question, the subnet is 192.168.100.192. Alright, I'm obviously talking you through that, but you remember we had to go through 5 different steps each time before to get a 5-minute solution. If I just opened up this question now and didn't do an explanation for you, I would have gone 24 plus 3, tick 3, tick 3, count up in 32, 0, 32, 64, 96, 128, 160, 192, 224. I would have found that the right answer, and I would have answered this in about 30 seconds. And we'll obviously pick up the speed as we go through. So this is the chart in action. I know we haven't covered this bit, but remember, in the exam, you don't get extra marks for working out how many subnets. They didn't ask that. If they did ask that, then obviously we'd come down to this part here, and then we may or may not have to refer back up to this part. So this was the introduction to the subnetting cheat chart. We'll be referring to this a lot through the rest of the course. Thanks for watching. Let's have a look at an example. We'll do some easy examples before we move on to harder stuff. This is a design question. How many subnets and hosts? So anything with like how many of is obviously a design question. Design questions go down here pretty much. We just may need to refer up to the upper subnets part. So you can see it's a Class C address, so you normally have /24. Remember the number at the start tells us. To get from /24 to /26, we basically add 2. So if 2 bits are stolen from our traditional subnet, which gave us 1 subnet and 254 hosts, we've taken 2 bits from the third octet. So this has generated 4 subnets. If we take 4 bits from, if we take 2 bits from this subnet, that leaves us 1, 2, 3, 4, 5, 6 hosts. So we've taken 2, and obviously there's 8 bits in every subnet. 8 bits in every subnet. So we've got 6 bits left for hosts. So 1, 2, 3, 4, 5, 6. That gives us 64, and we take 2 away, 1 for the subnet and 1 for the broadcast. So 62 hosts per subnet. So this mask, taking 2 bits from the standard, gets 4 subnets, 62 hosts per subnet. Next question, you're given an IP address of 192.168.5.0, the standard subnet mask, and you need to subnet this address to make 8 subnets with 30 hosts per subnet. So 8 subnets, each with 30 hosts, and we've got a standard Class C address network looking at the number. So all we do is we want to get to this 8 number. So all we do is tick down the subnet value, and we see we tick down 3 places to get us our 8 subnets. So in order to work out what the mask is in longhand, we tick down 3 the same. Whatever we tick down here, we tick down here. So we've taken 3 bits. So our standard subnet mask was 255.255.255.0. We've taken 3 bits, which gets us 224. Or if they say what's the CIDR value, it was 24 bits. We've taken 3. So 24, 25, 26. It would be a /27. If you take 3 bits from the third octet, fourth octet, sorry, that leaves another 5 because we have 8 bits in each octet. So 1, 2, 3, 4, 5, and for hosts we have to take 2 away. So that got us, find my marker, sorry. That got us our 8 subnets, and each subnet has got 30 hosts in. The answer then was the 255.255.254. Okay, so let's look at an example. I know this technically isn't a question. It doesn't say which subnet is this particular host in, but we're going to answer 2 different questions just using the chart design and the subnetting. So host 192.168.1.200 is the Class C address, so obviously our host address, specifically the network, is going to be here, and the host is going to be in here somewhere. We've got a /25 subnet mask. We should have a /24 because it's a Class C, but we've added 1 basically to get our subnet mask. And actually, you know what the subnet mask is because it actually says it in there. It's put it out in longhand. And if we steal 1 bit from here, we steal 1 bit from here to get our increment. So our increment is 128 and we're allowed to start off at 0. So our first subnet's here, and our second's here. Obviously host 200 is going to be in the second subnet. If you wanted to work out your host, not that it asks, your first host would be 129, and then you go all the way. We don't have another subnet because there's only 2 subnets with this particular value, so you'll go all the way. You know that all the host bits filled in binary is going to be 1, 2, 3, 4, 5, 6, 7, 8. You know it's going to be 255. So if you take one away, it's 254. So all the host numbers, again, you weren't asked this, I'm just showing you how the chart works. All the host numbers go from 129 up to 254 inclusive. Host number 200 is in there. Now, if they said, oh, by the way, you know, what's the broadcast address? Well, you know that. What's the subnet address? Well, we know that. If they said how many subnets and how many hosts are generated, you already know we've taken 1 bit for subnets. So you know we've got 2 subnets because we've counted them here. And that left 7 bits for hosts. 1, 2, 3, 4, 5, 6, 7. And we take 2 away. So 2 subnets, each with 126 hosts. Now, I know the question didn't ask it. I'm just showing you how easy it is to get all the answers you need just by working out how many bits have been stolen, and then going over here and ticking 1 in this case, 1 in this case, and obviously 1 down here, and all you've got left, you just tick down here. It's really that simple. So I know a lot of people look for extra bits or extra levels of difficulty. Obviously the questions can get harder, but the process over here never changes. So we've got another question. This time it's /26, or in the question, for whatever reason, they've given us the subnet mask in full, which they do sometimes. Now I know I haven't got an IP address here. I just want to do some more work on showing you how this chart works. So we'll presume it was a Class C network and they've applied this 192 mask. So up to this bit we've got 24 binary bits, and you know they've added 2 to get 20 to get to 26. So anytime that happens, anytime any number's added, you just tick down the amount of numbers added, and you can see that corresponds to 192. We already knew that, but what we didn't know is what increment our subnets go up in after 0. And our subnets will go, let's just do the last octet here. So it would be whatever the address is, network, 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 and then host. So this is the host part here now. So we know it's going up in increments of 64, and we'll keep going in increments of 64 until we get to 192. I've actually done this quite a few times, so I know, you know, it'll take you a while to work out this, but eventually after you keep adding up in increments of 16, 32, 64, whatever, you'll get to the answers pretty quick. So I can see we've got 4 subnets, 1, 2, 3, 4, sorry. However, just to confirm that 2 bits were stolen, gives us 4 subnets, we can see here. If you were asked how many hosts, well, we've taken 2 bits out of 8 octets, so that leaves us 1, 2, 3, 4, 5, that leaves us 6 bits for hosts. So 4 subnets and 62 because we need to take 2 away for the broadcast and the subnet. So we've got 4 subnets, each with 62 hosts, and our subnets are 0, 64, 128 and 192. Our host will be the first number after, so 1, 2, if you take 1 away from 64 to get the broadcast, and then 1 away from that to get your last host. 128 if you take 1 away to get the broadcast from the last subnet. 1 away to get your last available host, and then the first host is 65. 192, you take 1 away, and you take 1 away to get your last host, and your first host is 129, and then your broadcast will be 255, all the bits turned on. Last host will be 254, first host will be 193. So these are all the possible questions that you would be asked in the exam using subnetting. Now there's different types of question for route summarization, which we'll cover later. But all the subnetting questions and all the design questions will really boil down to all of this, and what you'll normally have to do is either use that top bit or either use this bottom bit, depending on which question you're asked. So welcome to our next question. Pretty standard exam type question. Which subnet is host 200.100.206.99/27 in? This would typically be a Class C address, looking at the number, and you would typically have a 24-bit mask, because that's the rule from the RFC. 24 plus 3 gets you to 27. So let's just tick down 3. Now they didn't ask you to write out the subnet mask in full. I'm showing you the subnet mask in full, but they didn't ask you to write it out. So that isn't part of the question. I've ticked 3 down here, so I ticked 3 across here to get me the increment. Now beforehand, what we used to do is we used to take 256 away, 224 away from 256 to get the answer. But now we're just using this chart. So our subnets are going up in increments of 32, and we're allowed to start off at 0. So 200, 100, 206.0. And by the way, in the exam I don't write any of this stuff because I know it's a Class C. I don't write any of this, I just write 032. I'm doing this for your benefit. 100, 206.32, 200, 100, 206.64, 200, 100, 206.96. We've got the answer. I guarantee that 99 is going to be in this subnet here. In the exam, go 1 past, just to sanity check, especially when it's a low number that you're climbing up in. We're okay here. 206 plus, what do we go, 96 plus 32. We would stop now in the exam because you got the answer. The answer is 200, 100, 206.96 is the host that this is the subnet that this host is in. I'm going to write out all these subnets for you, so you can see me applying everything that we've learned. 200, 100, 206.160, 200, 100, 206 dot add 32, 192, and I know our last subnet's going to end in 224. 200, 100, 206.224. Alright, so we've got 1, 2, 3, 4, 5, 6, 7, 8. Why did I count the number of subnets? We've stolen 3 bits in the last octet, So if we haven't been asked, I'll just keep stressing this, we haven't been asked to do this, but I'm going to show you how the chart works. We've got 8 subnets, and I just counted them. You saw me count them. So we've taken 3 bits for subnets, leaving us 5 bits. 1, 2, 3, 4, 5. Take away 2. So we've got 8 subnets, each with 30 hosts. And if you wanted to, you could count the host numbers. So the next subnet is 32, so the broadcast is going to be 31. The last host number is 30. The first one is going to be 1. 30 hosts. 30 hosts. I'm just proving that the whole system works. So I could do this for everyone. I'll just do it for the next one. 33 is going to be the first host. 64 minus 1. 63 is the broadcast. And 62 is the last host address. And you could do this. I recommend you stop the video and do this for every one so you get some practice. But basically we got the answer about 3 minutes ago, which was basically ticking 3 down, ticking 3 across, adding up in increments of 32, starting off at 0 until we got to the correct address here. So I'm just giving you extra value here so you know how to apply everything from the top and bottom. Alright, so we've got a new type of question. They're trying to catch us out here. What is the broadcast address for the subnet that this host is in? Well, it's a class C address. We should be using /24, but we're using /28. So to get from 24 to 28, we add 4. 1, 2, 3, 4. The mask is 240. Not that they asked us that, but we need to tick down 4 so we can see our increment of 16. Now we're looking for a host in a subnet that's 167. So what we're going to have to do here is jump. And the reason we need to jump is we're going to be counting up in increments of 16 until we get to this particular subnet. That's going to take too long in the exam. So can we agree that if we kept on doing that, and if we did it 10 times, we'd get to 160? You know, if we did 16, 32, 48, etc. My maths isn't particularly good, but I know if we did it 10 times, we'd get to 160. Now we need to go to the next subnet because I'm pretty sure our host is in there. And we need to add 16 to that. We're doing that so we can get the broadcast address for this subnet, which is 1 away from this subnet. So you take 1 away from the next subnet. Our broadcast address is 190.200.200.175. All right, stop here in the exam. Don't do anything else because you will see the answers here and you will tick the correct one, which is obviously this one here. However, I'm going to carry on now just to show you how the rest of it works. The first host will be 161. The last host will be 174. So we've definitely confirmed that our host is inside that subnet there. You can do this for all the other subnets if you want. There's probably too many actually, but you can do it for the other subnets if you want. We've stolen 4 bits up here. Whatever you do up here, you'll do down here. So 1, 2, 3, 4 subnets. We've got 16 subnets. And we've got 4 bits left for our host per subnet. We take 2 away to get 14. we've generated, with this mask up here, /28, we've generated 16 subnets, and each one has got 14 host numbers. So that's all the information that you would ever need in these types of questions. But just remember, in the exam, stop when you get the answer, because unlike when you did an exam at school for mathematics, you get extra credit for showing you're working out. You don't get that in the exam. So we've got our stock exam style question here. Which subnet is hosting? So we know any of these which subnet is the hosting, which is the broadcast address, etc. We're going to the top here. It's a Class C network. You recognise that from the number. And the 24 is the standard mask. We've got 29, so to get from 24 to 29 we add 5. And that's what we tick here. If they wanted you to write out the subnet mask, you'd write it out in full, 255.255.255.248, but they didn't, so we'll just work out now the increment. Our subnets are going up in increments of 8, and we'll start off with 0. 200.155.0 is the first subnet. 200.155.8 is the next one. We're looking for host 86 and we're counting up in increments of 8. Now this is obviously going to take us a bit too long, so can we agree if we carried on counting up in increments of 8 we'd get to 80? I hope so. So that saved you about 60 seconds in the exam. I think our host is in here. 100.55.88 is the next one. So now it's guaranteed. This is our host. This is our subnet, sorry. In the exam, tick and then stop with this question and then move on to the next question. However, I just want to add some extra value for you in case you get asked something else. We'll work out the broadcast address, etc. So our next subnet takeaway 1 or -1 is 87. Take 1 away from that, 86. Our first host is 81. So our hosts in this subnet go from 81 to 86. It looks to me that the hosts have got 6 subnets in. We'll confirm in a minute. Now I'm going to go down here again. This isn't in the question. I just want to train you how to use this chart, so we might as well kill 2 birds with 1 stone. If we've stolen 5 bits here, we do the same here. That tells us how many subnets we have. If we've stolen 5 bits out of 8, that leaves us 3 bits for hosts. 8 minus 2, 6 hosts per subnet. Which subnet is host 210.25.200.165/30 in? This is still Class C address. To get from /24, to /30, we'll add 6. So 1, 2, 3, 4, 5, 6. If you had to write the subnet mask out in full, it would be 255.255.255.252. However, in this question we're not being asked, so we'll tick across 1, 2, 3, 4, 5, 6 to get our increment. So our subnets are going up in increments of 4. Starting at 0. Now, can we agree that we're going to be a long time counting up in increments of 4 until we get to 165? So I know if I carried on counting, let me see, if I carried on counting up in 4s, I'd get to 8. I could get to 80 eventually because I'm counting up in increments of 8, and I could also get to 160. There's no calculators in the exam usually, but I know that 160 is an increment of 4. I've kept the increments going to 80, then 160. You just don't have the time in the exam to count in 4s all the way up here. Just make sure you get the increment correct. Next subnet 210.25.200.164. This looks like the subnet because the 165 will be the first host. I'll just sanity check. 168. Alright, so the answer is the host is in subnet 210.25.100.164 as per usual. Stop what you're doing and tick the question and then move on. Just for extra working out, 167 will be the broadcast, 166 will be the last host, 165 will be the first host. It's pretty clear here that we've got 2 hosts in our subnet. So these are generally used on point-to-point links. So if you've got a router here and you've got a serial cable connected to another router here, you would normally use a /30 mask, which is what we've got here, because that gives us 2 host address, .1 and .2, etc, etc. So you can do the other working out if you want, what is the first host, last host, broadcast. I just wanted to go down here just to demonstrate. 1, 2, 3, 4, 5, 6. We've got 64 subnets, so now you can see why we shouldn't be counting up in increments of 4, because we'd be doing it a long time because it's a late number. 64 subnets, and each subnet has got, we've got 2 left because we've ticked down 6. 4 minus 2, we've got 2 hosts per subnet. So this, I just wanted to go through briefly, is the class B possible values and subnets. And as we already know, a class B address is fixed thus. The first 16 bits are for the network. The next 16 bits are for hosts on that network. So there's another 16 bits here. These are fixed. We can't steal network bits. The only time you would show a less value is the case we already discussed, which is supernetting, which means advertising your routes, which has got nothing to do with subnetting. However, we can steal bits from this side, as we know. So if we didn't steal any bits, we'd have our default mask of 16, which would give us one network with over 65,000 hosts. If we stole 1 bit, which I'm going to show you in a minute, that would give us 2 networks, and you can see a smaller amount of hosts. What gets interesting is we then get to what looks like a Class C mask, because all of these you would think, hang on, this should be along with an address such as 192.168, whatever. But there's no rules for subnetting. A subnetting for Class B can use what would normally be recognized as a Class C subnet mask. These are because of the VLSM and CIDR, which means you could, if you only needed 2 hosts for your network, then you could use this mask here if you had a Class B address. That's absolutely fine. So these numbers, the more network, the more subnets you have, the fewer hosts you have per subnet because you've got less bits available. Alright, so I've got an example here. I don't have an IP address. It doesn't really matter for this question. I just wanted to illustrate something. Now we've only got one row of bits here. If I wanted to do a class B address, I'd have to write this out twice because we've got 16 bits. We've got 8 bits here and 8 bits here. So what we need to do is just pretend that we're working on the third octet, and this is what we've captured here is our third octet in here. And this is where we're doing our subnetting. Later we're going to do some subnetting on the fourth octet. So what will happen is this whole box here is here at the moment, our subnetting box. It will shift over to here just to save time and to get answers in the exam. It'll make more sense when we do it. So let's just play along with the question here. We had 16 because it's a class B. Somebody's taken 1 bit to get us our mask, which we've seen 255.255.128.0. That means we tick across whatever we tick here, we tick across here. We've ticked across 1 to get our increment, and our subnets, remember, are allowed to start off at subnet 0. So our subnet would be 0.0.255.255.128.0. If you wanted to do your working out, you saw in the previous chart that it got us 2 subnets. That leaves 15 bits for host, which is why I don't think you'd ever see this being used. I think I've got enough space here maybe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Alright, so that would give us 2 subnets, each with 32,766 because we took 2 away, host per subnet. You can come back to this example later. It's pretty rare, if not never used, because it just gives you too few subnets and too many hosts per subnet. But I wanted to go through it because it's still one of the possible values. So let's get back to a standard type of question. Which subnet is host 150.200.155.23 in? We know we're working with class B now, and you know anyway, because you can see the first number is 150. Instead of /16, we've got /18, so pretty easy to work out. We need to add 2 bits, so we've stolen 2 bits. Now remember, we're stealing bits from the second octet here. There's obviously a third octet. There's obviously a fourth octet that goes over here, but really we don't need to put 2 of these together. There's no point. You can put a +8 or just remember. So we've taken 2 bits here. The subnet mask is 255.255.192.0. If you tick across 2, because you tick down 2, our increments are going up in 64, and we're subnetting on the third octet. So 150.200, first 2 bits for class B are network bits, stuck. We're subnetting here, and we're allowed to have 0 in our first subnet. We're counting up in increments of 64. And we will continue to do so until we get to 192. .128.0 and then 150.200.192.0. Now we're looking for host number 155.23. Technically the whole lot is the host number on an interface, but 155.23, not in here, not in here, in here, because it's obviously more than 128 and less than 192. as per usual, stop what you're doing, tick the box, whatever that, it'll be one of the options. Just for completeness now, let's work out the first host address. Now I might run out of room here. We start off adding host numbers in the end here. We're subnetting from this end, but our host addresses we add here. So our first host, let's go down here, sorry, just for room. Our first host, 128.0 is the subnet we're on. First host will be 128.1. If you go to 192.0 and take one away, you'll get our broadcast. So that'll be 191.255 will be the broadcast on this subnet. Our last host number will be 191.254. So we've obviously got a lot of hosts going in here. I don't have enough room down here. I got rid of the other chart because there just wasn't enough numbers. But you could tick down here. How many places would you tick down? We've stolen 2 bits, so 6 here plus 8. You would tick down 14 places to work out how many hosts per subnet. And obviously you already know if you've stolen 2 bits, we've got 4 subnets. 1, 2, 3, 4. Alright, you can do some more working out with that if you want, working out all of the hosts, the broadcasts, etc. Let's continue with our Class B examples. As you know, you have a default mask of /16 for Class B networks. We've got /16 and we're trying to find this address here. So to get from 16 to 19, you add 3. Our mask, if we wrote it out, would be 255.255.224.0. And we've stolen 3 bits. Remember, we're working in the 3rd octet here, so if you want, you can add a little +8 there just to remind yourself, but it won't change anything. Our subnets are going up in increments of 32. We are subnetting, we have stolen bits from this 3rd octet. Because as you know, I keep telling you, these are fixed. These are available. Alright, so we can start off at 0 and we're looking for a number that has got 67.200 in. So 160.24, we can start off at subnet 0. 160.24 what we counted up in 32.0. In fact, I think we're almost there. 160.24.64.0. I'm almost certain that's the answer, but just to make sure. Add 32, 96.0. Okay, stop what you're doing in the exam, tick that box, and then move on to the next question. I'm going to carry on just so you can see what I'm doing and how many subnets we got. We haven't got too many with this mask, but I won't be able to do this next time. If you add 32 to 96, what do you get? 96, 32, 8, 1, 2, 8. I did know that, I'm just having a bit of a decaffeinated moment. 40, 128, 32 is 160. We can go all the way up to this number here, 224, which is the subnet value. 160.24.192.0. 160.24.224.0. 1, 2, 3, 4, 5, 6, 7, 8. We've stolen 3 bits from the 3rd octet. 1, 2, 3, and there you go. We have got 8 subnets. If we've stolen 3 bits, that leaves 5 bits in this octet and 8 bits in that octet. So 8, 9, 10. we've got 13 bits to tick down. Unfortunately, I didn't leave enough bits. I'll have to use this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 8192. So 8 subnets with 8190 because we have to take 2 away. Be careful in the exam because they'll trick you. One of the answers will be 8192, and in your excitement of getting what you think is the right answer, you'll probably tick it. Don't. You have to take 2 away. All right, I did more working out than I had to, just to show you again how the chart works. I'll probably stop doing that from now on, and I'll just focus on getting you the correct answer for the exam, which we've already seen here. Welcome to the next example, Class B network for all of this section actually. Which subnet is host 190.50.100.200/20 in? Our /16 address has gone up to /20, which means we've added 4. We're working in the third octet still. We're just stealing bits from this third octet here. So what was it? 4, 1, 2, 3, 4. Our mask would be 240.0, meaning 4 bits have been stolen, 4 bits are left, plus 8 bits in the last octet here. So we tick down 4, we're going to tick across 4, and we're going to work out our increments on the third octet are going up in 16 value. So it'll be 190.50.0.0, 190.50.16.0, 190.50.32.0, 190.50.48.0, 190.50. What are we, 16? 64.0, 190.50.80.0. I don't know why I picked such a high number now. 190.50.96.0. This is going to be the subnet because we're looking for 100.200. 190.50. If we add 16. 112.0. Alright, so we've gone past what we need. Tick this box in the exam, 190.50.96.0, and then move on to the next question. Next question, which subnet is host 180.22.56.65/21 in? It's a Class B network. We've gone from 16 to 21, so we've added 5 to get there. Oops, sorry, 21. We've added 21. So 1, 2, 3, 4, 5. Our subnet mask would be 255.245.248.0. We're subnetting on the third octet. Later on we're going to move across to the fourth, but let's not worry about that yet. 1, 2, 3, 4, 5. We're counting up in increments of 8 on the third octet, and we need to get to host 56.65. 180.22.0.0, 180.22.8.0. I can't jump up to 80 because we're looking for host 56. 180.22.16.0, 180.22.24.0. I could jump up here, but I won't. 22.32.0, 180.22.40.0. I should have jumped from 8 to 40, so when you do it in this 8 count, you can jump to 40. 180.22.56.0. It's going to be in this subnet. I'll just do the next one to make sure. Add 8 onto this, 64.0. Alright, so here's the answer. The 180.22.56.65 is in 180.22.56.0 subnet. I'll let you work out the first host, last host and broadcast if you want to for extra practice, and I'll see you on the next example. Which subnet is host 180.160.85 in? It's a class B network, so we know that this is network, host, and then we've stolen some host bits. Normally you'd have a /16, we've got a /23, so to get from 16 to 23 we've added 7. So we know now that we tick down 3, 4, 5, 6, 7. Our mask would be 255.255.254.0, and we'll tick across to get our increment 3, 4, 5, 6, 7. Now we've got a low increment here. Oh, and by the way, we're subnetting on the third octet, so just remember, it won't affect how you do anything, but just remember this is octet 3 here, and then octet 4. You'd write out the chart again, but there's really no need. 180.100.0.0, and then we're going to be counting up in our increment of 2.0. Now we've got to get to 60, so it's pretty much pointless counting up in 2s to get to 60. It would take forever. So 2.0, 4.0, 6.0 takes too long. Can we agree we would get to 60.0 if we carried on counting in 2s? I'm sure you do. Which is actually the subnet we're looking for. 180.100.62.0. Alright, we have our answer. Host 180.160.85 is in subnet 180.160.0. The first host would be 60.1. The broadcast would be one away from the next one, so 180.161.255. Then your last host would be 180.161.254. If you want to, you can tick down 7 places here, and then it would be 9 places down here to work out how many subnets and hosts. But you weren't asked that in the question, so we'll move on ahead. Which subnet is host 130.100.200.121/24 in? This might look strange. It doesn't matter what it looks like. We carry on doing what we have always done. To get from /16 to /24, we add 8. We're still working in this third octet here. In fact, we've stolen all the bits. available, but we can do it because the math works. So our third octet would say 255. Our subnets are going up in increments of 1. So if you got asked this question in the exam, you could actually answer it really quickly. 130.100.0.0, 130.100.1.0, we counted up in ones, 130.100.2.0. Shall we stop there? I think we should, because we know eventually we're going to get to 130.100.200.0 and then 130.100.201.0. We're going to keep going until we got to 255.0 because that's our subnet mask. Yeah. Alright, so if you wanted to, you could work out, this is obviously the answer here, so tick that in the exam. You could work out the first host, 200.1, the broadcast, which is 200.255, last host 200.254. You could do all that if you wanted, but we've got the answer to this question. Which subnet is host 190.20.56.65, 255.255.255.128 in? Well, this is the class B address, which is normally /16. It looks like we've filled all the bits up here, so there's 8 bits been added there, and then one more bit being added in the last octet. So we're in the 4th octet over here. There's no point in using this is the 3rd octet because we've still got to go across one. So you can see 128. We've stolen 1 bit from octet 4 to get us to /20 16 24 25 /25. Our subnets are going up in increments of 1 to 8. Now this is a strange one, and because remember everything happening behind this chart is in binary. So if you look at the decimal and look at the results we get, they're not going to make sense. But if we worked all this out in binary, it would. 191.20.0.0. So even though we're working on the last octet, we can have the 0 subnet. These are the rules in the RFC. Now, when we come on to do some more subnetting later, what my advice will be is to ignore octet number 3. If your subnets have spilled over from 3 into 4, and the same for class A, just focus on the last octet. And you'll see why in a minute, but I've got to show you the longer way just to show you how the math works. So this could be our first one, 191.20.0.128. Our last octet is going to be in increments of either 0 or 128. We've got the 255 here, which is counting up in ones. 191.20.1.0. 191.20.1.128, and this is what's going to keep happening. 2.0, 2.128, 3.0, 3.128. Every one value in here actually has 2 parts, a 0 and a 128. Again, you're going to be scratching your head if you look at that, but if you wrote all of this out in binary, if you had hours of extra time, then it would actually make sense because you're filling in the host and the subnet bits. Anyway, we're looking for 56.65. If we carry on counting up in increments of 1 and then 1.128, we're going to get to 191.20.56.0, and then 191.20.56.128. Clearly, we're in this subnet. And if you wanted to get the first host, let's just, for shortness, write this bit out. 56.1. You can see our broadcast is going to be 56.127, which is one away from here. Last host 56.126. Alright, so I know it's a head scratcher. If you're still stuck, come back to this later when you've got a bit more experience, because we've got more examples to get through, and if you really want to, you can work out the binary. Which subnet is host 180.100.220/27 in? Class B address, so it should be /16. We've got to /27, so we've added 11. So we've gone subnetting, we've filled in 8 bits from this octet, and then we're using 3 bits from this last octet. 8 plus 3 is 11. So we've moved over to the 4th octet here, which is where we are now, and we've spilled over 8 bits to 9, 10, 11 bits. So our mask would be, because we've used all these 8 bits, 2, 2, 4. And if we go down 3, we go up 3. Our increments are going up in 32s. Right, I'm going to show you this 180.100.0.0. This is going to be absolutely awful for a bit. 180.100.0.32, 180.100.0.64. We're going to keep counting up in increments of 32 until we get to 0.224. And then the whole nightmare starts again. 1.0, 1.32. You're going to go all the way up for every single one value here, because we've got a 255 here in the 3rd octet. We're going to be counting up in the 32 octet in the 4th subnet. So this is going to be pretty soul destroying. So let's do something else now, which is going to make life a lot easier for you. And we're going to do, remember I said in the exam we're not designing networks for customers, we're answering questions. The computer doesn't care what you do. Nobody cares what you do. The only thing we care about is getting to the correct answer. So do you remember I said earlier that Class B networks and Class C networks and A, they don't really matter too much anymore. This is only a historical value. But what it's good for subnetting is telling us how many bits are stolen. So if you saw the 180, you think, well, hang on, I know that's a Class B, so I know bits have been stolen from here and then here. So let's forget about what class we're using, and let's just think about what number we're using. This tells us that we've spilled over into octet 4. All our subnetting, really, the important stuff is going on in this octet. So let's just say we've got 3 bits from this last octet stolen, which we've done, and that means we tick across 3. So let's just fix the first 3 numbers, 180.100.1.0. 180.100.1.32. 180.100.1.64. Alright, so we're going to keep counting up in increments of 32. What I'm going to do is I'll do 96 and then I'll double it. So 96 times 2, 180.100.1.192, 180.100.1. Add 32 to that, 224. Alright, so we've gone past the answer, the subnet, sorry. So the answer is going to be host 180.100.1.220 is in subnet 180.100.1.192. Got another class B problem here, but you can see we've got a mask that goes into the third octet. So we're going to carry on with our cheat. So 3 lots of 255 gives you 24. We've got 28. I know we've got 8 bits in the last octet, but let's just do our quick cheat. So we've got 24 bits so far. To get to 28, we've added an extra 4 bits. So our mask is 240. 1, 2, 3, 4 is the same value. We're going to count up in increments of 16. Starting here. Now what we could have done is gone 150, 60, 0, 0. 150, 60, 0.16, 0.32, and we'd have whatever 8 values per number. So we'd have thousands of subnets, and we've got quite a few hosts per subnet, but nowhere near as many. Oh no, not many hosts per subnet actually. So we can't do that in the exam. So we'll fix the bits that have got 255 in, and we'll focus on finding this number by counting up in increments of 16. 150.60.200.16. In fact, we're going to do a jump strategy in a second. 150.60.200.32. Let's jump up to 150, 60, 200, any increment of 32. I'll do 96 because it looks like that's more acceptable to get to this host. 60, 200.112. Alright, we've got the answer. 150.60.200.96 is the subnet that host 107 is in. You can see because it's obviously 107 is more than 96 and less than 112. So in the exam, tick that answer and let's move on. Just wanted to start off our Class A section with all the possible subnet values. The default mask, which comes with every Class A network, you've got your /8 mask or .255.0.0.0, which gives you one subnet and 1.6 million hosts on that subnet. And as per usual, as you start taking subnet bits, this number here will increase. You'll get more subnets and less hosts. On also note, we go from our standard address mask here to the end of the second octet, to the end of the third octet, and all the way what you would normally consider to be a Class C subnet mask, for example, /26 or a Class C network with extra subnetting. So we're forgetting about classes. The only time we are thinking about classes really is just so you know which number is fixed. The first, the second, the third the fourth, and then you can work out how many bits are stolen. Are they stolen from here? Have they been stolen from here? Or finally here? So that's the only reason we're really thinking about classes of addresses. Now, we'll start off with a pretty easy example. Which subnet is 10, 100, 193 in? We'd normally have /8, but we've got /10. So obviously we've added 2 to get from 8 to 10. So all we do is tick down here. We weren't asked, but you would write out 255.192.0.0 if you were asked, otherwise don't bother. Because I've ticked down 2, I'll tick across 2 the same, and our subnet increment is 64. And we're looking for host 100, and we're subnetting on the second octet here. So as per usual, you can start off with 10.0.0.0, 10.64, 10.128.0.0. In the exam, obviously stop. No point in doing any extra working out. You clearly can see that host 10, 100, 193 is in here. So don't do any more working out, because it's just a waste of valuable time. The last available subnet, because this is the subnet value, is here. You can work out first host and last host if you want. First host will be 1064.0.1. The broadcast will be 1 away from the previous one, so 10.127.255.255 is a broadcast on that subnet. Last host will be 10.127.255.254. So obviously in our last 4, 5, 6, 7, in our last octet here, one of the bits is turned off, and in the second last one, 4, 5, 6, 7, 8, in the last subnet, all of our host bits are turned on in here, in here, and here. I mean, all of the host bits. This is why it looks a bit strange when we write it out in decimal. So our answer is which subnet? That host up here is in subnet 1064.0.0. You haven't been asked to work out hosts and how many hosts and subnets. You've obviously stolen 2 bits, and there's over 4 million. If you tick down all the way through all these octets, you'd find there's over 4 million plus hosts per subnet. Alright, so that's the end. I'll see you on the next example. Welcome to our next example. Obviously we're still working on Class A addresses, and we've got 10, 210, 204, 70 and /12. Normally we'd have a /8 and we've got /12. So to get from here to here, we add 4. So if we've added 4, we'll just tick down 4 places here. Now I only say this in case they ask you to write out the subnet mask, which would be 255.240.0.0, but they didn't, so I'll just tick across 4. This gets us the increment that our subnets will go up in, and we're subnetting on the second octet. So we're going to count them in 16s until we get to this 210. We can start off at 0. 10.16.0.0. I think we'll probably have to jump here. 10.32.0.0. Now if you multiplied 32 by 6, you'd go up to 192. So I'll just do a jump here. 10.192.0.0. I'll add 16 to that. 10.208. This looks like our subnet, but let's just check. 10.224.0.0. Okay, so this is our subnet. Host 10.210.204.70 is in subnet 10.208.0.0. Another class A, 10, 200, 100, 107, this time /20. So our /8, we've added, it seems, quite a number of bits in order to get to this /20 address. Enough, as a matter of fact, to take us into the third octet here. So to get from 8 to 20, we add 12. Obviously, we don't have 12 places here, so we've gone past the second octet, and we're now into the third octet. So 8 and then 9, 10, 11, 12. I'll write this out for you, not that it was asked. So this is our standard 8 bits. This is a stolen 8 bits. And then we've got the other 4 bits here, which gives us our 240. So 4 bits here, and then 0. And then 4, 1, 2, 3, 4. Our increments are going up in 16. Now, we're allowed, the way the RFC works and the binary works, we can start off at here, and we're working on this third octet. So what happens is it makes it quite awkward to work out. We go 10, 0, 0, 0, 10.0.16.0, 32.0, and we fill in this third octet all the way up until we get to 240. Now, I'm showing you the easy way to subnet, so we're not going to do this. Anytime you see a 255 and more bits taken for the next octet, fix it, subnet it. So what I'm telling you to do is fix 10.200, because you would get to this anyway. If you carried on doing this for about 30 mins, roughly, you would eventually get to this point where you've hit the 200 subnet, and you'd go 10.200, 0, 0, 10.200, 16.0, 10.200, 32.0. I'm going to jump because I can count up in increments of 16. So jump 10.200.96.0, 10.200, what am I doing, 16, so 112.0. Okay, so we have hit our subnet that our host number's in. Host number 10.200.100.107 is in subnet 10.200.196.0, 96.0. Your first host, if I just, haven't got much room, so your first host would be 96.1. Your broadcast would be 111.255. Your last host would be 111.254. And if you were designing, you would have a chart for every single subnet, and then every single allocation hosts, and then every single broadcast. Obviously, this would be a lot of work for you, but in the exam, we were just concerned with getting the answer. So we got the answer in the quickest way possible. See you on the next question. Got another class A address here, and instead of our standard /8 mask, we've got a /26. So to get from 8 to 26, we've added 18 places, and we're subnetting on this last octet here. So what we're going to do is just go straight through to the quickest way to answer the exam. We've obviously already got 16 bits added in the previous 2 octets, so we've spilled over, and in our last subnet we've got 192. and we've gone 2 over into the last octet, so we've obviously got 16 bits already in the previous 2 octets here, so 16, 17, 18. So our increments are going up in 64. Instead of starting off at 20, 0, 0, 0, we just don't have time, so we'll treat everything with the 255 in as fixed. It's not fixed in the last octet, so in the last octet we'll go up in increments of 64. 20.100.55.64. Obviously host 3 is in the first octet. So we got the answer, tick that and then move on. This host with this subnet should be /24, but we're at /28, so we add 4 bits, 1, 2, 3, 4, 1, 2, 3, 4, our increment 16, 192.168.0.0. We're looking for 244, so we'll go 16, and then we'll use our jump strategy to get to 160, then 176, this is the last octet obviously, 192.208.224, 192.168.1, so I should put 1 here, 1.240. This is the last octet, the last subnet, and our host is in this one here. We've got /27 mask, so we're just going to treat this as bit stolen from the last octet. So to get to /27, 3 bits were taken. Obviously it's a class B, so we've already got bits taken from the last octet, but we don't care. We've got 3 bits taken from the last octet, and our last octet will go up in increments of 32. 172.16.27.0, 172.16.27.32, 172.16.27.64, 172.16.27.96, 172.16.27.128. Okay, our host is in this subnet 172.16.27.96. You can't, it's been given this address and requires 4 subnets. Each subnet must be able to provide at least 10 hosts, so 10 or more, but we do need 4 subnets. So 1, 2 gives us the 4 subnets, 1, 2 gives us the mask. That's the exam answer, and that leaves 6 bits, 2, 3, 4, 5, 6. We've got 4 subnets, each supporting 60 hosts, which answers the question. You have this address with a 24-bit mask. The customer wants at least 9 subnets and each must have at least 10 hosts. So we need to get as close as that as possible, but not less. 4 ticks gives us 16. 1, 2, 3, 4 ticks will give you the mask 255.240 or /28 if you're counting in bits. That leaves 1, 2, 3, 4 bits for hosts. 16 subnets, each with 14 hosts. We have a Class B IP address with this mask. We require 30 subnets. Each subnet needs 1,000 hosts. So 1, 2, 3, 4, 5 gets us 32 subnets. 1, 2, 3, 4, 5 gets us the mask. So it could be /16 plus 5 is /21. We've taken 5 bits, so 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bits left to give us 2046 hosts per subnet. Welcome to the Wildcard Mask tutorial. We're going to cover the what, the whys and the hows of wildcard masking. Now what are they? Basically it's an inversion of a subnet mask. So you would look at your subnet mask 255.192.0 for example, and it would be an inversion. So it's as if somebody's taken it and swapped it around. I'll write out the answer here. And then I'll explain it later on. Basically, it does match the subnet mask in as much that if you added the top number to the bottom number, you would always get the value 255. That's the easiest way to answer the questions in any exams. So why do we use them? They're actually used by firewalls and routers. So for example, if you have a firewall checking traffic from the internet here, and say it's got access list, it's used to match certain types of network traffic, and you can check the subnet mask and network against the wildcard mask. Also used by routing protocols. If you're using, for example, OSPF, you will configure a network number, but you will also configure a wildcard mask. This tells the protocol exactly which networks and subnets you want to advertise, and you can be very specific with your configurations, because some networks you won't want to be advertised, others you will want to go out to the internet or wherever else. So how do we do it? If you want to match all traffic from the 172.16.2 network, then you would add the wildcard mask 000255. So what happens here is I'm written it out in binary. A 0 means match. We're concerned about what happens when there's a 0, and I've written this out in binary 172.16.20. Match everything here, match everything here, match everything here. We don't care what happens. So this could be any value after 172.16.2, and the values would be obviously everything from 1 to 255. Alright, here we have an access list permitting traffic from the 10 network. So anything from the 10 network. This is Cisco configuration, by the way. Different protocols will use graphical interfaces or command line interface. However, the rules will still be the same. Whatever happens, you still need to know how to work this out. So permit 10.0.0.0, and it's saying 0 match, don't care. Next access list 12, permit 172.16.2.0, and then don't care, 0.0.0.255. So it could be anything after this, anything after the zeros, don't care. Access list 12, permit 192.168.1.0, 0, don't care, don't care, don't care. Access list 12, match anything that starts with 10.4, the rest don't care. If you wanted to deny the 192.168.100.96, now this is a bit difficult because we're using variable length subnet masking, so we're not using the standard /24 here. So we need to work out the wildcard mask. It'd be 0.0.0.31, and it makes more sense if we write it out in binary. So you can see this is our actual subnet mask written out in binary, and all we're going to do with the wildcard mask is invert it. Anytime there's a 1, we'll swap it for a 0. Anytime there's a 0, we'll swap it for a 1. Next example, 10.1.64.0, and this is the subnet mask that goes with the particular network. If you wanted to permit or deny this subnet, you would need to create a specific wildcard mask, and it needs to be reversed. So all you do is write out the subnet mask 255.255.255.192, and you add a number to it that's going to equal 255. So you add 0, and it gets you 255. You add 0, it gets you 255. You'd add 63 here to get 255, and then you'd add 255 to get 255. So this is how you get your mask 0.0.63.255. And there we have it in binary. What wildcard mask would deny the subnet 172.16.32.0 if it says 255.255.240.0? So instead of /16, we've got /20 network here. Well, if all you do is write out the subnet mask 255.255.240.0, you add a number that gets you 255. You don't need to add anything, don't need to. You'll need to add 15 to get 255, and you need to add 255 to get 255. So your access list would be 172.16.32.0, 0.0.15.255. Alright, that's the end. Please take the quiz. So welcome to our overview of IPv6 addressing. If you want to be in IT, I would have said from any time sort of 2016 onwards, but you needed to know like a little bit of knowledge, probably, you know, for the last few years. What is the address? How is it made? Well, you bear in mind now that around 30% plus of internet traffic is IPv6. And in the next few years, basically, we're going to be swapping from IPv4 to IPv6. So your level of knowledge is around here now, and very soon is going to have to be up here. So it's really important, and I don't know why, but most people seem to be avoiding learning it. The students I'm speaking to, the engineers, well, these people are going to be in trouble. So it's really important. It isn't too hard. And actually, compared to all of the rules and weird things that we see happening with IPv4, like having to reserve addresses and work out all these different ways of conserving addresses, like private addresses, and then using NAT, we don't have any of this with IPv6. And also, because there's an almost infinite amount of addresses, we don't have to worry about wasting them so much, so we're probably not going to have to worry about having point-to-point network links and all this kind of thing. So why do we need it? We ran out of IPv4 addresses some time ago, and now we're just spinning plates trying to keep it working with network address translation, the private IP address, RFC 1918 stuff, so the 172, 16 to 30, the 10 network, etc. And variable length subnet masking, so chopping our network into smaller parts. So the improvements made, there's many actually, and cleaved addresses, obviously there's a huge amount. You reduce the size of your routing tables, improve security. There's a plug and play, so you can just ask all the interfaces to self-configure. There's a multitude of things available and features. Now for Hex, just a little overview again, we covered it earlier. We know we've got 10 fingers, and if we started off on finger, calling it 0, we'd go 0, 1, 2, 3, 4 on your left hand, and then 5, 6, 7, 8, 9 on your right hand. Binary, we've talked about before, we use because signal on the wire can only be one, it can only be on or off. And so this generates our ones and our zeros. Hex is a kind of halfway house. It's something that can be kind of understood by humans with some practice, and it can be understood by machines also. So it's a kind of compromise. And it's, as you'll see soon, it's the only way that we could really write out IPv6 addresses. Binary is going to be impossible to understand for humans. So if you look at the base numbering systems, 10 is obviously, we got our 10 column when we worked out in school, our 1 column, sorry, which is our units, our tens, our 100s, or our thousands. Binary, we start off with 1, 2, 4, 8. Hexadecimal, we're to the power of 16. So our first character, our first number would represent the 1 column, and then however many 16, say for example we've got 1 in the 16 column, 1 in the 256, and then you'd obviously add these together to get your answer. And we covered this earlier on. You can, if you want, I probably would help in the exam if you've got time. I wouldn't write this out until I've got this type of question, binary to hexadecimal. You might have one of those exams, there's a bank of say 500 questions, and in your exam you're going to get, let's say you get 60 questions, so you might not get one of these type of questions, so it would have been a waste. Otherwise you could start off with your chart, decimal, binary, hex, 0 to 15, which is 16 characters. You could write out your binary values, and obviously this is 16 if you add all the numbers together. And then, 15 if you add all the numbers together, and then hex, you start off with 0 to F, and then this will help you do any working out. The address format for IPv6, there's several RFCs if you really want to look through them. It's 128 bits in length, typical exam question, broken down into 8 sets of 16, separated by a colon, so value here, colon, value here, colon, value here, colon, when written in your full format. So every 4 hex bits can range from nothing to everything. This is the lowest value for hex, obviously. This is the largest value for hex. So these, if you have your colon between here. Now some addresses are reserved, like for multicasts and other routing protocols, and for global routing and and connecting between your interfaces on your network. So you can't just add any address you wish. So you'd have whatever you have here, FFEE 010A, whatever, and these will all be separated by the colons here. I'm not going to write them all out, there's just too many values now. CIDR for IPv4, you can obviously do IPv4 you can obviously do the longhand. What's going on with my writing today? Or you can do CIDR. And normally when you're writing stuff out on interfaces, you actually have to write it out in full, but you can represent it in a CIDR. In IPv6, it's just so long, it has to only be in CIDR. So you'd get to this part here of the address, which you won't see as a network engineer. So the global unicast, and then if you were given this part of the address, you've got /32. If you get this address here, you'd have a /48 mask, and then you would be allocated probably this part. You might have a chunk of this part here, so there might be another division here of another 16 bits added, and then the rest might be for hosts. It just depends how big your organization is. IPv6 address representation. There's 3 ways to represent your address and the address, and this is the typical exam question also. So the preferred or complete representation or form, you can compress it, and then IPv6 with a embedded IPv4. So in your IPv6 packet, inside here would be IPv4 and 4, the rest would be IPv6, and then probably if you're doing some sort of dual stack, it would get to your router, it would strip off these 2 parts if this network's running IPv4 only, and this is going to happen until we finally replace IPv4. So the preferred format is the longest format, also referred to as a complete form. You're probably not going to be writing this because it just takes too long. Imagine addressing your entire network, and it's all the characters. The preferred format for writing an address is a series of 8 16-bit hexadecimal fields separated by a colon, and here luckily is one I wrote earlier, so we've got all of our fields here, and we've filled each one. Each one has 4 values. There's nothing taken away, nothing added, and there's no abbreviation. So these are the types of examples. If you want, you can pause the video and just look at all the values that you could use in all of the fields. Now we can compress the address. This is just a utility, a way to make life easier for us as network engineers, and you need to know it in case somebody hands you a compressed address and says add it to the interface. Now the first method lets you use this, a double colon, to compress consecutive 0 values in a valid address. So you can only use one. You can only use this once. So if you see this anywhere in your address, or if you're trying to compress it, you can't then add it later on, or you can't have it anywhere earlier in the address. That's what I just said. So if we look here, we've got consecutive zeros all the way. You wouldn't normally have this address probably. So what you can do is basically say everything before this is a 0. And here, in this part of the address, we can see we've got consecutive zeros. So we can legally, if we were writing this address on an interface, we could say 2001 : and then carry on with the rest of the address. And the router or switch or whatever, the Windows PC, would let you input this value. And here we have it again, consecutive zeros. And we've got it here this time. And so it's been added here, and I'm sure you get the gist. And finally, just in case you do get asked, you can use all zeros as an address, and you could just enter that as the, funnily enough, as the IPv6 address. Now, method 2. This allows leading zeros to be omitted from the IPv6 address. Be careful. These are leading zeros here. These are trailing zeros. You can compress it, this part. You can't compress this part, so don't get caught out in the exam. Obviously, if you tried it in the real world, it print some sort of error message saying illegal or you can't do it. So if every bit in the 16-bit field is set to 0, then 10 must be used. So there must be at least 10 somewhere in this field. You can't have nothing. So let's have a look. We've got some zeros here, so we've managed to just represent that as 10. Here we've got a leading 0, so we've just put the 1, 2, 3. Here we've got a leading 0, so we've just put the 4B0. This is a trailing 0, so we can't get rid of that. And see, we've got one here, the 00 CD, so instead we've just got the CD. You can see we haven't tried to do it in the middle of the 2004 because these aren't leading zeros. Now that you can actually combine these, I don't know if I've put it here to all together. So this is method 1 plus method 2. So method 1, remember, is a set of consecutive zeros, and method 2 is the leading zeros. So here we've got lots of consecutive zeros, so all we've said is, there you go, that everything before that is a 0, and then we get further along here 000C, so we've just put the C in the address. Here we've got some double set of zeros here, so we've put it here, a double colon, and the 00 CD, we've just put CD. So if you've got access to Packet Tracer or a home network or some sort of interface where you can input these addresses, have a go yourself. Do not try this on any internet-facing machines or devices, because you could actually allocate somebody's IPv6 address and then you could get in trouble. Alright, so we've come to the end. Take the quiz and I'll see you on the next presentation. Welcome to our brief discussion on subnetting IPv6. First thing is, you don't actually have to subnet IPv6. There's so many available addresses that the concept is actually discouraged in some of the documentation if you read it, because that gives you or creates the impression that you need to conserve addresses because you're going to run out, where the case is actually that you're not going to run out of address. It's next to impossible to do so. So we'll just go over a couple of points here. As you already know, IPv6 addresses are allocated to companies with a prefix. So the host part of the address is always 64 bits. So this these 64 bits here, we've already said it's 128, are for hosts. So this is always the case. The standard prefix is usually /48, which gets you around here. This leaves 16 bits free for network administrators. Now this depends obviously on where you're getting the addresses from, who you're getting them from, how big your company is. So just check. Now the same rules apply to both IPv4 and IPv6 in as far as the network addressing is concerned. One network per network segment. So you couldn't have, I'll shorten it, but you can't have a router here and say your network, I'm just going to reduce it to one character, say your network is A, you can't then use network A here because it's in use. So you'd have to apply a different network, use a freely available network address you don't have to pay for, or just apply for another one. Address allocation. Now, say for example you're allocated, I'm going to change this number in a minute for something a bit easy. This address is occupying 3 sections of the full IP address, and each section or quartered is 16 bits. So you've used 48. The host portion requires 64, so this leaves you the section I've already said around here to allocate to subnets. I only mention this in case you get a subnetting question in the exam, whichever exam you're taking. So if we go here, if we allocated all of the available addresses in hex, bear in mind we've got 16 bits to play with in hex here, you've still got over 65,000 possible subnets, which is, I'd say, almost mind-boggling, even for the largest networks I've worked on, which span the globe. And that's still an awful lot of subnets. So you simply start counting up in hex from 0, as 0 is legal, and keep going. And for your host you do the same. So let's look for, I've made this a bit easier now. You've got the, up here, you got up to the /48 here, and obviously the network part to here is 64 bits, and then this here is another 64 bits. So say you were given this portion of the address, the 48 bits, by your service provider, you would start a table or use your IP address allocation software and start allocating. And I don't know how many departments you would have. Subnet 0000 would go to your human resources. Next subnet to your admin team. Next subnet sales. Next subnet IT. Next subnet your research team. I mean, you'd run out of teams, I'm sure. But look how simple it is. If we do it this way, by the way, there are a number of other ways. You could actually subnet here. You could leave all of these as they are and just change the last 2 bits for subnets. This just makes it more complicated, but it is still legal. So I'm just telling you that. So you can see me counting up in hex anyway. A, B, C, D, E, F. We get to our last character. Let's go over to the next value in hex. 10, 11, 12, and so on and so forth, to the 65,500 and however many it is. So if you're like me and prefer the pictorial representation, I didn't allocate. You could obviously allocate subnet 0000. I didn't show that here in this diagram. So this is going off to your internet connection to a headquarters router, an internal router. You've got this network, the 03 network, the 05 network, and this 04 network. So this is just an illustration of how you could do it. If you go on to take design exams, for example, a Cisco Certified Design Associate, Professional, or Expert exams, which take several years of study, then you'd obviously go into this in a lot more detail. But we've certainly got enough to get us through most exams, I think. Alright, so we got to the end. Thanks for watching.